Airport, the landmark development in Myanmar, the Bangalore International Airport expansion, Ahuja Towers, Mumbai, Unilever headquarters in Indonesia. We welcome you, sir. Over to you.
Thank you, and very good morning to the wonderful team at Westco. And obviously, I have to give credits to CTBUH for creating such amazing platforms where we get to interact with the academia, which we don't get to do too often. So again, thank you all for the opportunity. I have about 87 odd slides to cover, so I think the sooner we start, the better. I'll just share my screen. Is my screen coming through to everyone?
Yes.
Yes.
Okay, fantastic. Let's start then.
Sir, can you press the hide button on the box?
Yeah, sorry. Still very new to the tech. Is that better?
Yes, we're good to go.
Great, excellent. Again, good morning, everyone. So I think in the course of the presentation today, the aim is to actually cover high-rise building facades, basic design principles, but also based on some past experiences of presenting to college, I'll also be covering a little bit of maintenance and access, because with high-rise obviously comes responsibility of keeping your building clean and shiny through its design life. So I'll cover some basic principles of how to actually approach building maintenance and access in this presentation as well. As a part of the presentation, I've just broken it up into sort of three components. We will delve into the history of facades very quickly, just to sort of give us a context of how building envelopes or high-rise curtain walls have evolved into their current form from where they were like 50, 100, 150 years ago. We look at some basic principles of what do we need to consider, so sort of a quick bullet-pointed list of things that we need to consider, and then I'll probably take a quick dive into each of those principles. And then given that it's really hard to cover everything I know in one day, I'll probably walk you through a couple of applications of how these principles were applied to different design conditions, project challenges, working in different geographies, different geometries, different building regulations, so on and so forth. So that sort of gives you an overarching idea of how facades generally tend to be approached from a design perspective, to its materiality, to its performance, to its execution. So moving back a bit, rewinding a little bit, I think facades, the way we see them today, all the shiny glass buildings in and around town, sort of changing the skyline every 5, 7 or 10 years, they were never the same. I mean, glass as a subject itself was quite nascent, and glass's application on building was fairly limited to what we see on the screen. So you may have those sort of large bullseye skylights in churches, or sort of stained glass application in mosques. Other than that, glass was limited to sort of blown glass applications to onto your dining table essentially. Where this all changed was somewhere in the 1500s, where the desire to bring in natural daylight into the built spaces became increasingly evident and desirable, and that's where flat glass and the way we manufacture glass today was obviously not the case back in the days. So again, people sort of look back to glass blowers, and essentially what they came up with was like, oh, you want a big sheet of glass? Fine, I'll spin my my blow pipe so hard that I'll get a big disc of glass essentially, and then you can use that glass. So the guy on the right hand side is essentially making glass for buildings, and on the left hand side you see the application of that glass. So if you can see my pointer, what I'm pointing towards is these little punts or bullseye marks, which is basically the center pane of the glass. So you get glass in essentially a large circular disc, and then you have to cut little square or rectangular pieces to basically then manually glaze them inside windows. Functional from a daylight perspective, desirable from a views perspective, perhaps not. Again, because of the manufacturing process, you didn't get the sort of clarity. You could only figure out whether it's day or night, and if it's day, you get some amount of daylight into the interior space. Now, come to sort of mid 1800s, things changed again quite dramatically with the Industrial Revolution sort of knocking at our doors. And what you see on the overview picture here is the Crystal Pavilion. And Crystal Pavilion had a lot of firsts. I think Tak must have walked you through how the first elevators were introduced to the world in the Crystal Pavilion. I think Crystal Pavilion also is responsible to introducing large panels of glass, but not as spun discs, but this time they're being cast into large sort of timber molds. So the inset picture that you see is essentially being like hot glass, molten glass being poured into a disc in pretty much a heated chamber. So I really feel sorry for all those three guys who are working in there. And by the time it solidifies, it achieves a certain module, a certain size, and the entire Crystal Pavilion was reverse engineered based on the size you could achieve with cast glass. So that was again almost a show of strength, where industrial revolution, steel manufacturing, steam engines, elevators are all sort of yearning to be introduced to the world. But then again, the technology was very limited at that time. Then comes this man, Alistair Pilkington, who basically introduced a linear manufacturing process of how to make glass. Now, by linear manufacturing, he basically used molten glass, pretty much similar to the way they used at the Crystal Pavilion, but instead of rolling it flat, he basically floated it over a molten bath of tin, where the glass achieves certain level of flatness, and because of the molten tin, it also retains its fluid state, so you can process it for larger volumes, larger sheets. That's where flowed glass, what we typically know glass as, comes from. The process is called floating process, or it's also in the honor of the man himself, it's called the Pilkington process. This is coming 100 years from 1850s to about 1952. And the rest is history. I think from that point on, flowed glass basically introduced a lot of inline processes, where we started adding tints to glass, where we started adding coatings to glass, which were all a part of the linear machine process that you see behind him in this picture. Now, while glass was sort of moving up leaps and bounds in its technology, in what it could offer to buildings, building engineering per se was also taking tremendous leaps towards high-rise buildings. So the building you see on the left is the General Insurance Building, a General Home Insurance Building in Chicago. I think this is probably credited to be the first high-rise, and Chicago is like the home of high-rises, and that's where CTBUH is from. And this building is essentially credited to be the first building that moved away from load-bearing construction. So you could have larger window openings, because you did not need the external walls to carry the load of the building down. They were just there for an ornamental purpose. It just basically provided a skin to the building on the outside. But although even with that said, I think there was still a lot of sort of Victorian architectural style that's very evident here. And Home Insurance Building wanted to showcase to the world that you can do a framed steel structure without sort of playing with your insurances, etc. Building on the right, Bauhaus in Germany, I think this could potentially be called as the first curtain wall. And the way it was achieved was to actually put every single component piece by piece. So you had the vertical steel frames, horizontal steel frames, sort of all bolted with a massive scaffold up, and then each of the glasses were individually handset in place. Again, the buildings are essentially the same in the way they are conceived, but you see the stark difference where this building starts using glass more prominently as the building's face, and you can start looking through the building, you can start bringing in more light into the building, and that sort of starts the journey of the curtain wall that we see today. So, I mean, essentially from early 1500s to today, I mean, we were building cathedrals out of little pieces of glass, and then now we're building technology cathedrals out of glass and no other material. So I think we've come a long way, and this, I think, is just the beginning. So that sort of gives you a snapshot of how the history of facades has evolved from where it was and where it is today. So I'll basically cover a few touch points on how to approach facade design. What are the sort of critical key parameters of approaching facade design? And from an architectural perspective, It's not obviously important to be fully aware of all those principles. It's important, apologies. So it's actually important to be aware of those principles, but you may not need to get into the nuts and bolts of it. So at least you can ask the right questions and you can leave the right provisions, and you can do an informed building designs along with specialists. So it's not that everybody's trying to contribute into a system with people not knowing each other's trades really well. So as far as design hierarchy is concerned, as with everything, I think you need to you need to address the most important components first, and then the next important component, and then the next important component in some sort of a hierarchy. So with facades, obviously, the structural integrity of the facade is the most important, because that's the only thing that's separating your exteriors to a more comfortable, environmentally controlled interior space. The next is the environmental aspect of it, where that's the only element that is separating the exteriors to interiors. So again, the properties and how it performs to keep the elements out while giving you a comfortable environment indoors is important. Aesthetics, which I guess is important to all of you. The building needs to look great. It needs to play around with materials, it needs to play around with geometries, and it needs to stand out in the city skyline and make a statement. Lastly, I mean, in practical world, this is not this basically inverses itself, but cost obviously comes right at the top, where after you addressed everything you want, you need to also assess how much it's going to cost you at the end of the day. So that's the correct sequence, where you start to make sure that it's structurally integral, doesn't fall apart, one typhoon, two typhoons, somebody hitting it, or a fire, etc. Next is environmental, third is aesthetics, and then finally you need to also be aware of how much it's going to cost you. That's the real world scenario, where we typically start, and again, not a point of discouragement, but this is the way things work, where we obviously have to look at the cost first, and then we see what we can achieve aesthetically within that cost. And then third is environmental, fine, let's get a LEED platinum or a LEED silver, or what U value can we buy within that cost. And then lastly, oh, come on, structure has to work anyway, so you need to make sure that that works. So that's the right approach. Real world approach is this. All of us as professionals are trying to change it, and I think there's been reasonable success so far. So I'll harp upon structure first. So, I mean, this is a great example. I think one of my earliest gurus in facade engineering gave me this example, that facade is like the rhino's skin. Now, you see it's almost armored, where, you throw something at him and doesn't really move the rhino. He can't really feel it. But when the rhino itself is moving, there are these folded plates on the skin that basically move around, adjusting to his movement. So curtain walls is something very similar. And the reason it's called a curtain, because curtain flows and blows around, but it still has its own integrity within itself. So the idea and intention of doing facades is that you have a building that can move about under seismic forces. If wind blows too fast, the building can move around, and the facade can jiggle about within that movement without taking on any of the structural loads, but accommodating all those movements. So, I mean, this is basically the ground basics of facades, probably the first picture I show anyone who basically is interested in knowing how to draw a real world parallel to facades. So with structures comes external forces on buildings, and I think this is equally relevant to structures as well. So we have forces like wind, you have live loads within the building, where somebody may decide to put a grand piano at the edge of the building, or somebody may decide to park a Rolls Royce on the parking floor on one particular floor. You have factors like dead load, which is the dead load of the building itself. And during seismic events, the building moves quite differently than it moves during a wind event. So I'll dive into each of these and what is the impact on the design of the facade individually. So with a typical facade on a high-rise, now high-rise are perceived a little differently than your typical ground +2, ground +4 buildings. So the idea here is to actually have the entire facade installed from the outside. And this diagram basically represents a typical one floor arrangement where what you see in red is basically two slabs. The man on the right sits on the inside, and what is identified as a panel, which is this component starting from here to here, is essentially one single curtain wall panel that goes in. You have what we typically call as vision that allows visibility to the outside, brings daylight in, and then what we call as a spandrel, which is covering all your services, all your structural edge. And this is where you observe buildings around town. You suddenly start seeing sort of banding that happens where everything is glazed, but you still start seeing what's happening in the vision areas, which is all the occupied areas, and the spandrel that covers all your services in the structure behind. Now, coming to loads, obviously building has its own weight. And as the building is built, there's some level of shortening that the building goes through. Columns tend to shorten over time because of its own self-weight. There is long-term creep that happens as well. Like I illustrated, somebody may decide to put something heavy on this floor while this floor is fully unoccupied. So this slab may deflect more than while this slab does not deflect at all. So that's what we call as differential deflection. So facade needs to cater to that. So there is joints and allowances within the facade that allows for that movement while retaining its environmental integrity. So you don't really lose air or lose or allow water to come in while retaining its structural integrity. With wind, the building moves by itself, but facade as a subset between floors has to play its role as a structural element onto the building. So again, facade getting connected from floor to floor has to look at criteria like stress and deflection. This is a very sort of technically nuanced element of facade designing, facade engineering. But then the idea is that each floor is dealt differently. And each floor is designed to be a stack by itself, and then the following floor is another stack on top of that. Now, with wind, the building basically sways left to right because of sort of wind gusts that basically push the building in a specific direction. So there may be a differential story sway. So one slab above and one slab below may deflect a little differentially. So the facade needs to accommodate that into the design as well. The principle again being the same, that facade is installed from floor to floor. And the idea being that wherever the connection happens with the subsequent floor or the floor below is where the movement takes place and the movement is accommodated. With seismic, the story is slightly different. There may be one floor or subsequent floor sort of moving in different directions because of the frequency of the movement. And here in this case, again, the principle being the same, that you have a differential movement that's getting accommodated only at the stack level or only at the joint level, where the facade still retains its integrity from the floor to floor connection. So I know I've thrown a lot of jargons for a very early morning like this, but we will cover this under Q&A if there's some specific questions that you have. Now, the second key role, so we've covered structure, which makes sure that facade is integral or sort of, it doesn't lose its integrity by itself, but also accommodates movement within the building. The next aspect that I would like to cover is environment. Now, again, we live in a very climate diverse country where, we have hot and dry, arid, humid climates to sort of torrential rainfall areas within the country as well. So, everything needs to be considered as to what kind of facade decisions you make while designing your building based on its geography. So rain obviously is the first element that needs to be dealt with as we are right now. Solar is another element where there are positive and sort of not so positive impacts of the sun shining down in your buildings. You may get decent daylight through larger facade openings, but that also invites heat gains. Wind is another factor. With insular buildings, there's a lot of air leakage that can contribute to loss of air conditioning, but also at the same time, wind can be capitalized to provide natural ventilation where desired. With environment also comes safety. You have fire issues where buildings catch fire, and facades tend to be the first to be blamed because you see fire coming through or billowing through a curtain wall panel. The other aspects, the other important aspects are sort of blast impact. So let's say, for very critical installations, government buildings, hotels, where you may have sort of unwanted visitors who, trying to create a havoc. So again, how does a blast impact your facade, and how can you design for it? And then lastly, there's projectile resistance. Say if there's a typhoon and branches sort of fly off around, how does the building deal with that? Because facade is the first interface that all the flying projectiles have. So coming to the environmental aspect, and I know there's a sustainability session later in the day, which I think, and an MEP session as well. So I think that you'll probably get more insights into this then. But I'll just cover some basics here. So apart from the benefit of the sun sort of bringing natural daylight, which I think is good for our emotional well-being, it also brings in unwanted heat, and I think glass boxes is what they call, saying they're not so suited for our tropical climate, so on and so forth. But I think if you make the right design decisions, you can sort of convert them into very effective design strategies. So with tropics, what typically happens, and this is completely polar opposite of what happens in more temperate climates like Northern Europe, is that we get heat conducted into building by sort of two modes. One is conduction, which is the ambient temperature on the outside that gets conducted through a physical element, which is your facade, and then gets radiated back into the interior environment. What is more critical for a tropical climate is the radiated heat gain, which is the amount of sun that comes through your glass, potentially heats up surfaces on the inside, which could be blinds, which could be carpets, which could be your desks, and then radiates the heat back into the space. So I think that becomes more critical to deal with. So, which is where we say that, shading strategies are extremely important for tropical climates, which is where glass selection, which is where external shades, etc., come into play. So to deal with U value, which is the conducted heat gain, I think we just need to improve the insulation of the facade. So uses of higher insulated materials, potentially use of double glazed units into your facades can deal with that issue, while lowering the SC value, which is the factor that controls radiated heat gain. That actually is aided by adding external shading or potentially using a lower shading coefficient on your glass products on the outside. So I think that basically ticks both the boxes, but it's generally a balance that you have to achieve, because with higher SC, you may have higher reflectivity on your glass. You may have some sort of tint to what you see on the outside. So I think the idea is sort of trying to find out what is the best balance your building can achieve. With water, I think the longest phone calls I've had with clients is about their buildings leaking. So I think water creates a bit of a menace, and with monsoons getting more and more intense in South Asia year by year, I think this has become a really important point to ponder over. So the buildings have to be watertight. So they need to be designed with multiple barriers within the system, and potentially this is a topic for another day, more like an advanced class. The systems need to be externally drained. Now, system needs to accommodate a little bit of water, but also it's important to drain it outward. And then lastly, I think your surfaces need to be drainable. They need to be self-cleaning. So having long ledges, etc., where the water can potentially be held back, they need to be avoided. Then lastly, air becomes a very important aspect, and how do we deal with winds and prevailing wind directions. Obviously, where desired, the buildings should be airtight. The system itself should be airtight, but where required, we could introduce passive ventilation through the facade, where there could be controllable grills or controllable ventilation equipment that could be introduced in the facade for better occupant comfort. This is always a sort of diversity between the commercial applications of facades on office buildings, where everything needs to be airtight, air conditioned, while residential buildings tend to have more operable windows, more desire to sort of bring fresh air in, and not needing to use the air conditioning all day long. Lastly, environmental aspect, safety becomes extremely important. So I think the first and most important aspect of high-rise design, facade design, is to make sure that you have adequate fire compartmentation between different spaces. So let's say I'm not responsible, I'm not a very responsible occupant of my apartment, and I leave something on which causes a fire. The intent behind the design should be that the fire should stay contained within that apartment and should not bother somebody living upstairs or living in the adjacent apartments. So what's sort of shown in the dark red, the deep cherry red here is basically a fire separation that happens between floors. And if there is fire separation required between rooms as well, that has a similar sort of fire stop application. Now, zone isolation becomes important, so does floor and room separation. But while coming to other aspects like blast impact, etc., including external projectiles hitting the facade, the integrity of the facade itself becomes important. Now, it depends what you want the facade to do. The idea here is to make sure that the impact or the kinetic energy that actually is exposed to the facade, that should not really impact the user on the inside. And that again is potentially a very detailed session for potentially another day. Now, we're coming down to aesthetics, I think probably the subject of interest of how do we achieve what we want to design or doodle as a building, and what can we do with facade technologies. So I think first thing that's foremost important is the geometry of the building. And geometry for facade design purely is a subject by itself, but I'll do a little touch point on the BMU section as well and how that impacts the maintenance of facades. Second most important element is the experience, like the inside out and the outside in. Now, with residential buildings typically, and to some extent other building typologies like hotels or commercial buildings, the inside out experience is very important, where the person who's really paying for that space should have a decent experience where he gets clear views, corner vistas, so on and so forth. And then there's the whole Instagram world where people are designing for building from outside in, where it needs to look great from outside, needs to have certain features from the outside for the world to see. Materials become really important, where there are the vision and the light components. So areas which you can see through, areas which bring light into the interior space, the selection of that becomes really important. The placement of that becomes important. There are certain opaque areas which I sort of highlighted in the previous section, which are called the spandrels, which essentially happen at every floor level, and what is the sort of strategy for those areas. Those can have glass application going on them. Those can also have other material applications going on them. And then lastly, there are features. You obviously want your building to have certain presence in the skyline. So I think it's really important to have certain features, but also trying to tie them in with other narratives, like that actually enhances the performance of your building at the same time. So now those are the sort of outline principles of what needs to be considered while designing building facades from a structural perspective, from an environmental perspective, and from an aesthetic perspective. I will have a brief touch point on what are the kind of technologies available for different kind of building applications. So the first, and I think building facades are manufactured. So they come from a factory, and factory is a very linear process. So you need to identify minimal optimal sizes. You need to identify as few numbers of typical sizes that you can actually put on your building. So there is some level of rationalization required. So when you have a highly complex geometry that you probably saw on the first slide of this presentation, where you have multiple different pieces because of the organic form, you need to look at optimizing them for manufacturing. You need to make sure that there are less 1 or 2 pieces, but there are more like 100 pieces of a type or 200 pieces of a type. So I think that becomes really important. Next comes, which I think is going to be the key slide for this presentation, is the system selection. Now, when it comes to external facades, there's a few ways and few methods to build it. They are largely driven by where you're building it, what's the kind of height of the building that you are aspiring to build, also the kind of geometry that you have on the building, and then largely, what's the kind of access you have available on site. So Typically, in our experience, about 95% of all high-rise buildings we've built is using the approach on the extreme left, which is using a fully unitized approach where everything is modular. So whatever you need to build into the facade, which could have external shades, which could have spandrels, which could have external light features, which could have photovoltaic cells, etc., all comes in pre-assembled in from a factory with very, very minimal work that needs to be done on site. So the idea here is maximum factory, minimum site. Because of high-rise limitations and high wind pressures and obviously safety being considered, we are trying to maximize the amount of work to be done in a factory and then minimum amount of work to be done on site, where you just hoist the panel as the diagram shows in position, fix it in place, and that basically provides you a watertight, airtight enclosure to your building. This is typically used for a fully glazed facades, but then we've done a lot of applications where other materials or features or complex geometries have been achieved with this facade as well. Again, one thing very important is there's no external access required, because as the buildings get higher, the possibility of being able to put external access in form of mast climbers, in form of scaffoldings, etc., becomes extremely difficult. The next one, which is in the middle, which is what we call as partly unitized curtain wall or a partly unitized window wall or a ribbon facade, basically takes cues from a fully unitized approach, but also respects certain restrictions of certain buildings. And there are few project examples which I'll walk you through that will illustrate the use of an example like this, where there may be cases that you may have projections out of the building, where you may have large terraces or you may have balconies moving through. So the intent of using unitized facade within that sort of becomes very difficult. So the idea here would be to still maintain horizontal level of unitizing, where all these panels basically come and interlock with each other in a linear fashion per floor, but still retaining level of unitizing with a break happening at the floor level. So here, what we're trying to achieve is partial external access, where you have some level of access required to be able to seal this. So again, not highly suitable for very high rise or super talls, but in case where you have restrictions of not being able to fully unitize it, this becomes the next best thing. So again, here we are looking at an optimum factory and only the interfaces to be done at site. So we're trying to still optimize the amount of elements we can do in a factory, and then only the interfacing elements, which is the top and the bottom edge, that basically gets dealt with at the site. Also called as ribbon facade, and then this requires partial access for just sealing the interfaces at the top and the bottom. Lastly, we have what we call as a site assembled or a stick curtain wall or semi-unitized curtain wall. There's many names to it. Again, here, given that we like having a lot of control on the product that gets delivered on the site, we're still trying to optimize the use of factory here. And we're still using interfaces to be dealt with at site. But then the intent here, as the diagram shows, is that all the framing, all the subframing gets fixed on site. And there are externally glazed panels which come pre-glazed as cassettes with a minimal aluminum frame that gets installed on site. Not suitable at all for a super tall or a high rise, but can be utilized for sort of mid-range buildings that can go up to 4 or 5 floors, where you can probably have a safe external access. But then this again requires full access, because you need to install the panels from the outside, and you also need to seal all the joints from the outside. So again, where the volume is low and unitizing doesn't really give you the kind of cost benefits, you can have a simpler system like a semi-unitized or a stick system that can be used here. Now, lastly, coming to the top of the pyramid or the bottom of the pyramid, depending on the way you look at it, costs. I could potentially consume the whole day talking about how to achieve the right cost balance, but I think costs are largely system and skill driven. And it also sort of varies from project to project, depending on where you're building it and what you're trying to build. But again, we could delve in more details during Q&A if somebody is curious about this aspect. So, having touched upon sort of the outline theory, I think it's also important to see how these principles are put in application. So, working with different architects, working in different geographies, I bring to the table a few examples, a few built and some underbuilt examples of projects which we've worked on. Where we had different sort of challenges, but then we sort of had to use different tools to cater to those challenges. This unfortunately is an unbuilt project that I was involved in back about 10 odd years ago. This is a headquarter building for Pertamina, which is the state-owned oil company of Indonesia. The centerpiece is a 523 meters tall tower, along with a couple of ancillary buildings around the campus. Now, with tall buildings, I heard this saying somewhere that everybody's trying to design tall buildings like perfume bottles, like they all have to have like a unique shape and they need to be very organic spires up in the skyline. So yeah, so I mean, this was no different. But in this case, what seemed like a sort of almost square base with like a curved segment that was extruded straight up to 1 to 2/3 of the building height. And then the top 1/3 of the building basically starts receding back, but also reducing in floor plate. So this sort of derived circular geometry also starts reducing in floor plate. So this starts to look elegant, really simple, but also at the same time, it starts posing challenges like how do you deal with the geometry like that? And when you are trying to panelize geometry like this, like it's almost trying to take a stack of business cards and trying to paste them on a gym ball almost. So, you want to have flat panels because they're cheap, cost effective, but at the same time, the geometry doesn't allow you to do so. So imagine if I were to put two panels in this area of the building, you would have this slight gap because the building geometry starts curving around, not only in plan, but also in section. If it curves around in one plane, it's always achievable, but it curves around, if it's a double curve, then it always becomes a little tricky. So with the panel height of 4.3 meters with 1.5 wide modules, we had to find a solution for the client. So we looked at a number of options here. Firstly was to triangulate it. So it's almost like segmenting the entire surface. We looked at bending the entire facade, again, extremely expensive. We looked at stepping. So curvature only happens in one plane while we step the facade back in the other plane, which is in section. And then lastly, which was a really innovative way of doing it, which is to fish scale, where you push the panel back, but you fill the triangle in between with something. We basically looked at everything with across feasibility, aesthetics, and cost, obviously all three of them being extremely important. And we thought that we really needed something that ticked all the boxes. So all the three fields should be green for that. And then we looked east, we looked far west, we looked somewhat shorter west. This is the IAAC building by Frank Gehry in New York. And this is one of our buildings in Dubai, the Ocean Towers. And none of the buildings here have bent glass or sort of factory manufactured bending. This is all bent on site. So glass has this level of flexibility that allows you to sort of press one corner and then bend it into a certain shape. So with a lot of research, design team going back to subcontractors, all the way to silicon suppliers, fabricators, and then we brought back what was the level of comfort that they were okay with to actually corner bend the panel, just force fit the panel in place, and the number came out to be 20 mm. So basically we're trying to push one panel in and pull the other panel out to make sure that these edges meet without any mechanical bending or without any mechanical forming to the panel. So the other element was, like I said on the first example, where a lot of rationalization gets done on projects like this. And I think that's really important because they need to be designed for manufacturing. So the base case in this case, with the top third of the building, where we rationalized it using parametric tools, we were getting a total panel groups, which means the type A, the type B, the type C, totaling up to 118 sets, with repeated panels coming to 951 and 1,300 unique panels. So all of these panels that you see in the gray in the middle, they are all unique panels. The problem with that is if, let's say, one panel doesn't arrive on site or sort of breaks while installing it, then your installation just stops. You can't follow through to the next panel because your installation stops, and you need to get that panel back on site before you can continue it. So what we then did was to basically, instead of having these mullion joints aligning vertically, so vertical joints are all aligned as you see here, we decided to stagger them a little bit. So that actually gives you some advantages from a repetition perspective. So the staggering, obviously, you'll probably not notice it so well 300 meters up in the air. So I think the idea was that let's try and make the best use of geometry here. With that, we could bring the panel groups down to 96, repeated panels to more than 2000, and unique panels, which were all these corner panels, which are triangular in shape, which you can't really change anyways. They were brought down to 164. So I think such processes become really crucial, really critical for built forms like this. Next example I have is not much of a high rise, but it's equally fascinating from a material standpoint. In this case, this is, I think, a building along Hyde Park in Sydney, almost sort of an Oval Maidan equivalent of Mumbai, where what you see here on the first 3 floors, not so evident in this picture, there are these organic bands or organic spandrels per se, which are built in stone. And here's a better finished picture of the building. So this is basically an Australian local limestone that was being used in this building. And I think the idea was to try and propose other materials, but then the material was sold to the client and it was very, very integral to the narrative of the building. So it had to be used a certain way. So with that comes, like they say, with great power comes great responsibility. We obviously had to look at ways to make this more manufacturable. Now, again, complex forms with stone, you can only imagine how complex the entire design process can get. But I think trying to simplify the design or the approach to the building was step 1 to achieving this process, because each of these stone pieces basically milled out of a solid block of stone. So the idea was to actually make sure that there is more number of repetitions. Building being bilaterally symmetrical, we could get at least 2 pieces of each. And then each of these was initially slightly diverse with this sort of bottom edge stretching down, but we suggested that we should make them all identical. So, the installation process can probably continue the way it is. And then we basically modeled the entire thing in manufacturing software called CATIA. And with CATIA, the inputs to a 5D milling machine basically allowed us to procure the exact size of stone. So these pre-dressed stones arrive from the quarry with the exact dimensions required to actually achieve each piece. What may not be quite visible is that all of these panels are tagged here. So with each code being punched into the machine and the stone being put in place, this machine does its magic, and it basically carves out the not required spaces and gives you like a sculpted piece to put on a framework. Other challenges that happen typically in high-profile areas or sort of active high street retail areas is where you don't really get access to put up scaffolds or put up some permanent installation equipment. So the idea here was to try and make large panels, which basically arrive on site as these large panels with multiple stone panels installed on it. So we were even involved in designing a jig, which you can see here on the right hand side, and then the entire panel, which is 4 of these units per floor, were mounted on the jig with just 2 bolts to be undone, and the truck parked below the building. You could just hoist this panel straight up on the building, and with 2 bolts up on the building, you could install the entire panel. So, I mean, this is the entire geometry built onto sort of temporary jigs, all ready to be hoisted on a truck. So, yeah, great, sort of diverse example, really quirky way of approaching a unique problem. The next project I have is, again, from a market I've been really involved in, and what looks like a really sort of plain Jane, very vanilla building was supposed to be bearing a very unique brief from the client, where the client's brief was that I don't want this building to be designed for people to take pictures of it and post it up on construction vlogs or Instagram. I basically want this building to be designed for the occupant on the inside. Now, what's really unique about this building is, now when we typically approach curtain walls or when we typically approach external facades, we look at installing a typical panel floor to floor, as I demonstrated in the presentation earlier. where you may have a vision panel, you may have a rail here where your desks align itself, both of them being vision. You may have a spandrel panel here, which basically covers your services and your structure. But with the client, they did not want mullions or vertical frames happening at or so very often. So they really wanted to widen the vision, to widen the view. So every office is like a corner office. You don't really get that frame obstruction when you're looking out. So their intention was to actually increase the panel width. So your vision basically gets much wider, spandrel gets wider, the same case. But I think the challenge here is to have such a large unit, which basically becomes extremely heavy and difficult to transport, difficult to hoist and install. How do you engineer it like that? So I think the idea we came up with was to have two-part unitizing that's happening on every floor. So we'll essentially have unit number one, which is a spandrel unit, which is getting installed first, and then you have a vision unit, which gets installed from the inside. So the number of panels you install per floor from the inside is still the same, but then the idea is to actually get them as wide as possible. So in a typical high-rise scenario, and this building was designed to like Japanese seismic codes, the idea here was that we will have a day of about 10.8 meters. We get typical unitized curtain wall panels that are spanning anywhere between 1.2 to 1.8 meters in width. And with that, you get about 6 panels. What we could achieve with this approach was this. So you essentially have 3 large panels spanning 3.6 meters across. So your vertical frames are 3.6 meters apart. And you get a fantastic skyline view, almost with no frames blocking your view. And the clever thing that was done here is that you even have some color judgments being made here, where you paint your mullions black and you keep your horizontals white, so the mullions sort of become less restrictive or less of an obstruction visually when looking outside. This is sort of a corner view. And again, it was engineered down to the level where you have the spandrel unit mullions are larger because all your desks align along this level, while the vision unit was made much slimmer. So that's basically the area you look through. So desks, etc., getting aligned on all this level, you get a much nicer, much cleaner view to the city outside. One last, I think this is probably the second last one. One quick example I'd like to run through, and this is a good example in how to achieve panelizing or unitizing in complex geometry. This is a project by Leza Hadid in Beijing, China. And this is a building called Wangjing Soho. 3 blocks, 2 office blocks and 1 hotel block, and one sort of a club facility that sits here. Now, what's not so evident in this case is that this building was initially designed to be a fully curved, glazed and clad application, where Chinese developers are obviously very cost sensitive. So again, in their case, it was like, how can we make this building more cost effective? So I think the idea again in this case was that we'll try and keep the glazed component, which is the most expensive to convert to a complex geometry, as simple as possible. So the idea was to make it into a stepped geometry, where all the external face, which is forming your organic components, get dealt with in these curved metal panels, which are more cost effective compared to glass to actually achieve in a complex form, while all the glazed elements are kept dead vertical. So again, the idea was that we try and again break this into a program, because it's very critical when you have companies who are leasing the space in your building, for them to sort of being able to move in and start fit outs early. So again, we were trying to keep the glazed component dead vertical, but it can sort of bend around corners, which still is relatively cost effective. We are able to seal the building from the outside, and then you do all of your external elements as a separate program. So all of these can be installed from the outside subsequently as sort of fully panelized cladding panels that come into play. Now, with this, the keys were handed over to the occupants so that they could start the fit out works, with these works sort of continuing. So it's like a win-win for both sides. Now, what's not, again, very evident, and I'll probably take you back to this picture, is these ribbons are sort of, they are narrow, and then this set sort of get wide, sort of very classic Zaha approach to building design, where they get narrow and wide in the same plane, which is fine. But what also happens is in the center of the building, the cladding panels are sort of more or less vertical. But as they wrap around the corner, they get really, really shallow in an angle. They start getting more and more upright. So again, the idea was to start looking at making it more manufacturable. So the intent was to make sure that this is adaptive in nature, where you could have one detail that suits all different design conditions. So in this case, what we did was basically designed a small saddle bracket, which again is a clever way to innovate a condition that can work for all different areas. And then this basically just toggles around. It basically turns around to whatever degrees you require, and then you can actually achieve something as dead vertical as that, or something that's more horizontal, which happens around the corner. So this is basically a mock-up of this just to test the concept out on site. This is, again, I wouldn't say it's a curtain wall example, but you know, it was one of my first projects that I started with Inhabit. This is a project in Repulse Bay in Hong Kong. Again, a very high-rise development, sort of premium development, where the owners really wanted to reclad the building to improve its design life, but also to sort of start impacting the property value on the upside. So what was supposed to be a very straight-jacketed, boxy building, the owners wanted to add some value to it, so decided to add certain canopies and also to retile the entire building. I think the architect's intent was that, you know, instead of retiling the whole building, let's just play around with the geometry, let's just play around with the colors a little bit. So the idea was to actually have the surface of the core droop outwards, almost flare outwards, to create a canopy, which is to be done in, again, 3D milled stone. So the first challenge, so as you see here, I mean, this is basically 180-meter high-rise in basically just facing the sea here. So the idea was to have this surface with these two canopies, which are almost flaring out, attached to the two cores, so they become like a nice drop-off for visitors, providing rain protection to the two towers. So if somebody has to go from one lobby to the other, there's also a canopy provided for that. So to achieve that, obviously you need to have some kind of cementitious surface. So this entire steel frame was designed to basically flare the surface out using GRC panels. And then the cladding was done on top of that. The second challenge that we faced on this building was that the architect really wanted a dark tile swatch. The building's called Ruby Coat, so you really wanted something up here as ruby red, and then it gradually fades down to warm white. Now, this is typically achievable in like mosaic tiles, where you order them in pallets and you just slap them on your bathroom walls and you're done. But this is, it's a high rise. I mean, how do you do something like that? And that too with tiles that are sort of really sizable. They are like, you know, almost a foot by 4 inches each. So again, we turned to parametrics. We looked at a few different ways, few different methods of actually achieving the contrast, achieving the gradual fade without, you know, having to have like legible bands of, you know, where the course changes. And then we gave the radio controls to the architect, saying, hey, why don't you play around with the buttons a little bit and see when you're happy, and then we'll have an export out of that. Now, all of this is great, but then how do you take it to manufacturing? The idea is that you want to give the supplier, the manufacturer, sufficient information to package it correctly, and then the contractor who's installing it should have sufficient information to see where each box goes on the building. So, so parametrics is all fine. They're not aware of, or they're not very well versed in using these tools. So we had to boil it down to a simple Excel sheet, which actually identified box packages for each floor and how it all changes. And to test it, I mean, this was a mock-up that I attended in Tokyo, in Kyoto. There was a tile factory there where we basically laid out the concept to put it to test, and they basically cut each tile in quarter size and then basically made a full-scale mock-up of how this pattern would go up or rather down on the building from the darkest to the lightest. So again, that was a non-curtain wall, but again, from a design perspective, it starts exploring possibilities of what can be done with the kind of tools we have at hand today. The next building I have is not essentially a high-rise, but nonetheless a very complex building, and I would say a very evolved building for a single ownership. This is the headquarter building for Unilever in Jakarta. They were again struggling with multiple tenanted spaces around the city, traffic in Jakarta being bad as it is. They really envisaged that we want to move into one building where we have expansion space and growth space. So basically, this is a ground scraper. This is, I think, about 160 meters across and 6 floors, including the mechanical floors up there. So more like a ground scraper, and if I will, this is more like a shape-shifting ground scraper. So no two floors are aligned. This basically projects some floors out and recedes some floors in. So it starts creating these wonderful terrace spaces. Some cases they're accessible for staff to sort of go out, take some fresh air in. In some cases they're not. So with the kind of climate, we had our environmental team involved in this as well, where the architectural concept was still sort of very aware of the environmental constraints that they have. Jakarta being bang in the middle of the, sitting bang at the equator, the east and the west facades tend to take more heat. The east and west facade, take more drilling, while the north and the south facade will take some part of the heat or will be responsible for some part of the heat gain depending on the time of the year it is. So the intent here was to actually provide more shading on the east and west elevations, and the denser fins are actually placed on the east and west elevations, and they gradually fade out. So the fin basically stops continuing when it goes on the north and south elevation. So that's again a very sensible strategy of trying to put the resources where they're required more. And again, that starts to sort of showing a very evolved design language. Like I had showcased as my second technology, this uses a unitized window wall approach per se. So in this case, because of the floors moving in and out, creating terraces or creating soffits, the idea here was to actually continue unitizing along one direction at least, and all of the fins that come pre-attached with the panel basically get installed and the mullions lock themselves in. And then we basically have external sealing that gets done for a building which is reasonable in height. And then all of these external panels are installed, which form the nosing, which forms the definitions of each of the floors. Now, yeah.
So just to remind, we just have exceeded the time limit, but yeah, we can, if possible, so can you?
Okay, I'll try and wind up in next 5, right?
Okay, fine.
So, okay, so I put potential. Okay, this is really interesting. I have to go through this one. This is another high-rise in China that we completed about 4 years ago, and this has a sort of very complex geometry nuance, which is individual to each panel. So what we call as sawtoothing. So if you cut a section here, you will see a zigzag edge of the building. If you cut a plan here, you will see a zigzag edge of the building. So again, it's sort of a very climatically chosen approach and also from a view orientation approach. Now, with, again, coming to rationalization, we try and find method to the madness. So each of the panels here is classified as an A or a B or a C. So again, it's very easy to communicate to a contractor saying, I want 340s of A, 220s of B, and 97 of C's, and so on. So again, the building sort of under construction, and you see each of these as panelized going up on the building, forming the envelope. The vertical sawtooth, where the building gets pushed outside, where I think the geometry nuance is more to do with how far you can push the glass out, is achieved by having this cross bracing frame here. And then we try and keep the functional component, which is the unitizing component, back up at the base level. Some of the images from the factory where this concept was put to test. Do we have, say, another 5-7 minutes for facade cleaning and maintenance?
Okay, fine, sir. You can continue with your presentation, but what we can do is the question and answer sessions could be clubbed with the next speaker.
That's fine. That's fine.
Okay.
I mean, I'd really like to at least have some basic touch points covered under here.
Okay, fine.
So with facade maintenance and access, I think we'll just cover very, very quickly the need, the basic principles in one of the applications. I don't have too many. So why do we need facade maintenance access? Obviously, you create facade on the outside on a high rise. You need to do periodic cleaning, which largely depend on the country you are in, the kind of urban dust levels you have, the kind of rain streaking that can potentially happen. How often does it rain? There are bird deposits, etc., that needs to be dealt with. The other thing is that you have maintenance of any external lighting fixtures, that you may have vertical green walls that need to be maintained. In some cases, in some ambitious cases, there's BIPV that gets applied on facades. So again, that requires maintenance. And also, what's important is to actually have replacement of materials. Let's say a cladding panel gets dented or a glass panel breaks, or an external feature has a faulty component to it, or let's say a BIPV panel or a lighting fixture needs to be replaced, you require access for all of that. Largely, basic principles are the geometry, I mean, the shape and the reach requirement. What kind of building are you designing? What is its shape? What is its outline geometry? The kind of lawn space we have available, and the kind of building height we have. So I think that basically defines the geometry constraints. Second is basically the kind of technologies we have. You have two kinds of system typologies. One is a crane type system, and then second is self-climbing systems, which are more suitable for sort of lower high rises, not super talls. With shape and reach requirement, as you can see here, you can design a building as a clean extrusion that runs vertically up. You can taper it to the top, or you could have a tapered bottom. Again, all of them sort of having a differential reach requirements. In some cases, you actually create shadow zones, which again need to be reached, where your facade cleaning and maintenance equipment should have the capability to reach inwards and access those areas. Lawn space, what I call as a battle zone with all consultants, is where everybody wants to claim some space. So you can have something that runs along the perimeter of the building, or as identified in yellow, you could have something that sits on the core of the building. So that allows you to launch your equipment. Lastly, building height. And again, this is, I think, a really critical point for everyone to take note of, that, generally by a rule of thumb, 160 meters is the level to which you can do self-climbing systems, and above 160 meters is where you need to have integrated climbing systems, where the winch or the coiling mechanism is built into the machine itself. Two kinds of overarching technologies. With self-climbing up to 160 meters height of a building, you can use davit arms, which are these brackets installed along the perimeter, or you could have an external monorail which sits on the face of the building, where you can attach a cradle to it. With integrated climbing technologies, you have short reach and long reach. Short reach is where you have this machine sort of treading along the perimeter, the edge of the building, and long reach is when you can't manage to get any space. You can put it on core top, and then that basically has a telescopic arm which makes sure you reach all corners of the building. One quick and rather very complex example is a project that we finished, and this basically has everything that can potentially be non-desirable on a building. You have a double helix crown, which basically peels back and then sort of generates at the other side. You have a helipad, so you have no access to the core. Again, in this case, we had to use a sort of a helical track that basically moves through the core and then approaches or reaches the other side. This is what the finished product looks like. So you have two tracks and a rack and pinion system, so like a cogwheel system that basically moves it up or down the core. And this, I think, is probably the first selfie stick BM you can probably see, where it takes a picture of itself. Yeah, I mean, here's a quick summary. I don't think I need to go through this, but like Pam suggested, we can take up the questions in the next session.
Thank you, sir. Thank you for the wonderful presentations. The visuals and on each slides, the illustrations were very catchy, and I'm sure the students are yet to they are still absorbing the details of the facade. So the biggest challenge that we see in the high-rise buildings today is of course the facade design, which is the main process of installation of the facades, the techniques which are used, the different materials that are used for the facade designs. The another challenge that we also see is the logistical problems which are faced in installation of the facades, and also the stability with respect to the other loading systems on the higher areas of the high rise. So but now, because of the shortage of the time, so we would like to kind of club the question and answer sessions for the by the end of the next speaker. So now we would like to, if possible, sir, we can take one of the questions. So I hand over this to the moderator, Ms. Janisha, to take one at least one question. So, Janisha, you can take over this.
All right. Thank you, sir, for your
Sorry,
wonderful.
just a minute. Mr. Basim, can you stop sharing? Yeah, thank you.
Thank you, sir, for the wonderful presentation. We have a few questions from the faculty members regarding facade design. So, one of the questions is, how does the facade system operate at the detail level while addressing torsion, both directions, rotational sway, along with considerable lateral sway in vertical and horizontal direction? If any detail could be discussed, it would help the students in the studio.
Okay, I think let's park that question. I might choose to answer that in the next session where I can pull up a detail on the screen as well.
Okay.
But a very sharp question. I think it's a really interesting question where building movements and complex movements like torsion, etc., how they get accommodated within facades. So yeah, I'll pull up a detail certainly for that one.
All right, sir. And any insights on the stormwater system? Because the facade will be receiving a lot of water during the rains and all of that. So for such a giant surface, how do you deal with the volumes?
So I think what's really evident from research, and I think this has been a question where everyone thinks that facade being such a large surface of the large water-bearing surface, you will essentially have like a waterfall at the base of the building, but it's not the case. Where water that gets clinged on the facade, because of wind movement, it also gets detached after a while. So you don't have a large volume of water coming in.
All right, sir. And any insights with respect to materials from a sustainability point of view for facade design?
You might have to elaborate a little more on the question from a generative perspective, from a carbon footprint perspective, from a life cycle cost assessment perspective. I think there's you can counter everything, but I think there are certain materials that have more embodied energy than the others. So I think that becomes one of the aspects. A lot of materials that are used on the facade, which is largely aluminium, are highly recyclable. So I think that's, again, a big thumbs up from a sustainability perspective, where aluminium could be essentially reused for the same purpose after the building has been demolished, or it could be salvaged. Glass, not so much. I think the question has to be more focused towards, are we trying to achieve a cradle-to-cradle approach? Are we trying to achieve recyclability approach? Are we trying to have low embodied approach? So I think different materials tick different boxes within that.
Gautam, I just want to add one question to this. What kind of codes would you like these students to refer? I know now NBC is covering a large amount of glass as a material and facade itself into NBC. But other than that, there are prevailing international codes. So which codes all of us should refer and study, because there are Australian codes, there are British codes. So which one could help them to understand facade and engineering more closely by reading themselves?
See, it's a maze that is, it's really, I really don't want to push them into it right at the moment, because, I mean, British codes actually cover aluminium, steel, and glass really well. American codes actually cover coatings really well. Australian codes cover performance really well. But I think if they can manage to grasp everything that NBC has to say, would be a really great start, because I think NBC has evolved. 2016 was like, it basically came out with flying colors on the facade front, where it covered a lot about coatings, a lot about performance. So I think from an Indian perspective, NBC has been tailored to cater to certain design conditions that we have, particular to our country. So I think that will be a really good start. Once you get into that, then you start understanding different nuances, which could do with fire. Like fire has some really evolved codes in Europe, in Australia, in the Middle East. But actually knowing what our code says first will be a good primer for them to then venture out into other codes. So I think, memorize your NBC. That's a great start.
And I have one more small question. If I am installing a green wall on my tall building, what would be the landscape architect scope, and what would be the facade consultant scope?
Great question.
I have to catch whom where.
Don't catch me for anything. Catch a landscape architect. So I think landscape architects' role again, and most landscape architects, find it challenging to choose the right species or plant species for high-rise application, because with wind, I think also, there is issues with propagation, issues with growth, where butterflies don't come so up high, so you don't have pollination and other things. So I think choosing plant species, watering the plants, or sort of irrigation and drainage, I think becomes their part of the deal. While we will look at the fixity, the load transfer, and generally the system and how the building behaves. So if there's a framework required and a watertight surface required, that's something what a facade engineer would deal with. And then on the outside, how do you fix the planters, whether they come in these pre-installed cassette green wall kind of systems, or do you do a planter with a mesh above it that allows the green wall to grow? That's sort of dealt with on the landscape consultancy.
Thank you, Gautam. Thank you.
Okay, sir. On that note, we will take the rest of the questions after some time. On behalf of Westco, we would like to thank you for your time and for the lovely presentations. And we would like to present to you a memento.
Digitally, nice. Thank you so much.
Thank you, sir.
I can probably hang around, right, for the next one.
Yes, sir.
If you can hang around, Gautam.
Yeah, Suraj is here.
Yes, Gautam, I think you should hang around a bit. Maybe you can get some more insight from the MEP side.
Of course, much needed. Much needed.
Yeah.
Like, the precedence of having facade prior to MEP is a very good strategy, because the impact of facade on a building system is very, very important to understand. And I think Gautam I was there almost for about 90% of a session, Gautam. Very, very insightful information to the team, I think, for the students and also to the faculty, and also for an MEP engineer like me, who really considers facade to be the skin of a building for it to breathe and live through.
Thank you, sir. We'll be starting with the next presentation. Our next presenter here is Mr. Suraj Nair. Mr. Suraj Nair is a professional with overall 23 years of experience in wide range of specializations in building sector. He is the founder director of Grunt Designs Private Limited, an engineering consultant design firm providing MEP, sustainability and well-being solutions. He has an experience in the field of MEP design and construction management and has worked in some reputed international consultancy firms. Mr. Suraj has international construction exposures in the MEP field, and his stint in Dubai, where he was involved in building the world's tallest building, the JW Mark. He has a right mix of the design and construction experience, and presently has his own building engineering and sustainability design consultancy practice, that is Grunt Design Buildings Private Limited, located in Mumbai, Bangalore, India. His professional experiences, we'll just like to cover a few projects here. The commercial and retail, the office complex in Sri Lanka, the High Street Phoenix, Palladium, Mumbai, Inorbit Mall, Hyderabad, R Mall, Mulund. We welcome you, sir. Over to you.
Thank you, Shrutika. It's really an honor to be presenting to the young developers of the Indian construction industry, you can say that way. And if we can influence a little bit good design practice into the upcoming designers within your college, it will be something that it's an achievement for me also. So I take this as a positive start to engage with the students across and also the faculty members. So I will firstly thank Professor Anand to give us the opportunity, and definitely through CTBH, through Mr. Girish and Anuja, who's always been very supportive of getting the best of the best industry professionals to get engaged with the students across. I think that's a very good initiative from CTBH and teaming up with the Architectural College. And basically, you're in the molding mode of getting into the industry as you move out. So if you can get inputs from the industry experts, whichever best we can, it will always help the team to move forward and inculcate a buildable design rather than being a theoretical design. That's more important. Theory is something which you can always learn, but buildability is something that comes with experience. And if you can club theory and buildability, I think you are already ready to conquer the world. So, and also thank all the CTBH speakers who are already presented yesterday, and Gautam also today, and coming forward with my other colleagues in the coming set of presentations. So I think with this short start, should I proceed with my presentation? It might be boring for many, but I would honestly tell you this is a very, very important topic of MEP engineering, which is very important for the building to live through. So if you get bored, you may just ask me to stop, take a breather, have a glass of water, come back. But do let me know if things are working for you. Anuja is already having a glass of water. She started that. So I think with the start to this, let's keep a little lively, no problem. We can do that way. If you feel bored, just raise your hands. I can stop a bit for some time. I will try to keep it short for maybe 25 to 30 minutes of presentation, maybe add on additional time with Gautam as well, myself giving you more time to discuss on the interactions. I think with Gautam and myself going together, it will be a very good plus point to interact on facade as well as MEP together. Okay, I'll just start presenting. Do let me know if it's visible on the screen as it comes across.
Yeah, we can see your screen now. Yes, it's
Sure.
screen.
Okay, you may see these buildings, quite number of one. The extreme right being Burj Khalifa. For any MEP engineer, it's a dream to work on some of the big buildings. I have not worked in these buildings, but I have been in and around these buildings with my stint in Dubai. But as an MEP engineer, I think it's a dream that somebody have some experience of Burj Khalifa in their entire scope, or at least to understand the building, something like that. So that's just your dynamics about how the Burj Khalifa is in terms of what it's the extreme right. Probably I'll just give a little pointers to you. It's about 828 meters tall building. And I'm not the designer. I've just known whatever best I can know from my people across in Middle East and my friends. It has got a number of amenity floors to break the building the way it needs to be, because you can't design such tall buildings at one go. You need to have services at various points. So you have amenity floors at various sections, maybe at every 100, 150 meters. And then they break the services at various points. There are elevator banks that are at various sections. There are high-speed elevators at 10 meters per second. If I'm not mistaken, 14 meters per second going up to the topmost levels. So I think this is just the base in which the benchmark of tall building has been in the industry right now, considering the MEP perspective. So let's go forward. I mean, I've been cordially been explained and been invited into the design today. I'm really thankful for that. You can contact me on additional information at email address. If you need some more information to come through, I'll always be happy to help the team. And do visit our website to just have some interesting engagement on what we offer in terms of. Yeah, it's very important. You can see a ship that's in the sea. For me, and as I understand, as you architects also, you should consider the ship as your building life, as your project. You can call it as your life cycle of, because the building that you design needs to sail through for about 50 years, 75 years, 100 years, whatever the design life of a building. That's your building, and it has to go through a lot of environmental issues. So we call it as a sea storm. So if you look into a ship that is within a sea storm, or the entire journey of a ship within the oceans across. The architect happens to be the captain of the ship. So there lies a deep responsibility within the architect to really design a building which can sail through the lifespan of expected out of the building. Now, if you have a captain, you need the engineer. Now, the engineer does not mean just the MEP engineer. It also includes your structural, your MEP, your facade, because the external of your building should be able to take care of all the kind of loads that comes in. So it's a collaboration between the engineer and the architect that will help the building to sail through across the lifespan. So that's very important that you understand your responsibility of how important an architect is to the building, right from start to the end. And so just do not make buildings for the sake of looking them pretty. It should survive. It should have its own. I would rather say, right, make livable buildings. I think this is the most important point where most of my colleagues in the architectural side believe, it's a pain. And some are really upfront in saying that it's very difficult to work with you, Suraj, and with the MEP engineers. But important that there has to be a coordination. Yes, it is pain because with compliance to codes, with compliance to requirements, with the new standards evolving everywhere, there are a lot of changes in the building design that comes up. That's the reason why we call it as architectural engineering. When you say architectural engineering, you should encompass the entire architecture, the structure, the facade, the MEP, the elevators, the landscape, all under your coordination. Yes, your expertise does go into the architecture, but please be taking the responsibility of coordinating the entire the envelope of the consultants that you work with. So do not worry. It looks difficult going forward in the life. This is the most important aspect of a building to be successful. The architect should be ready to coordinate with all the consultants. What are the questions that we look before high-rise design? So just adding quite a number of ones. One being, inside a building, the diesel generator locations, tall building particularly, where you put your standby generators. Electricity is something that you get from your source from the supply company, whether it's Adani or in Mumbai it's Adani or Tata Power. But it always needs an alternate source for during, if there is a power off. So you need to put the diesel generators within the building or outside the building. But when you put it within the building, it has got a chimney. It's got an exhaust stack that needs to be planned. A tall building which goes 100, 200, 300 or beyond has its own challenges in terms of locating this big white elephant that you can call it. It's a big stuff that needs to put within the building line, or it can be put outside. When you put outside, you need to coordinate with the landscape consultants, the designers. And again, the look and feel of these DG sets are not an easy perspective or not an easy on eye understanding. So that's something that you definitely need to start with understanding with. Wind pressure, definitely on the facade side also, and also on the air side on the building. And then you need to look at the pumping strategy that you can come up with. Some more addition, you need to know the building construction aspect. How do you stage the building? Where do you locate the heat rejection device in terms of these are the air conditioning units? If it's a residential unit, you're expected that these air conditioning aircon outdoor, that means you're using your split units, you see your VRF unit, you need to place them at a location which is breathable in the facade. So here comes the coordination between the facade as well as the MEP engineer in terms of heat rejection device. If it's a commercial building, it needs some amount of central cooling plant and a central heating rejection. So you need to plan them probably on top of a terrace or in zones which are accessible. So for all these, we really look at an engineered approach for the building services. So an engineered approach is not just the mechanical engineer or the MEP engineer working to, but along with the architect support and the facade, where we really come up with an engineered approach. It needs to look at, an MEP engineer also should look at what the requirement in the property, complying to your local regulations, whether you can scale your operations in such a way that you need not install all the equipments together and it will be built later, because buildings may not get occupied completely. So, and these seismic supports. most important in a tall building is the sway of the building or the resistance to the earthquake. How do during earthquake, how does these services hold themselves? Because the problem that happens during an earthquake is when the building sways or it comes with a certain amount of movement, the supports give away, and these huge equipments or the huge distribution system may fall down and can cause more life issues than your building per se. It's very critical that we should look into the seismic supports. I'll just take you into what is the looking forward on this presentation. So I'm going to cover up more so on the firefighting design. I'm going to stress a little bit more on the firefighting design because a building should be safe to live and work with. For a residential building, you live in for 24/7 application. If you're a commercial building, you are there for about 12 to 14 hours in a day and five days in a week, sometimes 6. But it's very necessary that you should live in a very safe environment where you're protected from any possible hazards that can impact. So I'll spend some more time on the firefighting design. Then on the mechanical, in terms of the air conditioning thought process, I will not be running too much into it because I know we don't have that much time. But I'm just trying to plant a little seed in your mind as an architect. What should be the consideration then and with respect to MEP that you should be picking up? Something on the electrical, and then on the plumbing design of a tall building, and then the building management system. So building management system, you can say in a very crude way, you have your chowkidar or your watchman sitting below. In some of the residential building, he's the man who keeps on floating around, looking at your elevator operation. You'll go back to your pump room, switch on your pump in the morning session, see that it is filled up. You'll go back to your overhead tanks, go there, look. Imagine a building like 300 meters, 400 meters, 600 meters tall, 800 meters tall. How many watchmen would you place at how many floors for this to work? So it's a very crude way of saying that, but that's how you correlate with the building management system. We call as an intelligent watchman, you can call it. He's a man who can think. We have given them the intelligence for him to understand the building systems and then operate logically by virtue of sitting on a computer or on your iPad or on your mobile phones. That's how the intelligent building management system is a very, very integrated, important part in running a building. Okay, let's understand fire services. So when we start about fire services, what is firefighting? Firefighting is basically the act of extinguishing fire. So a firefighter actually suppresses and extinguishes the fire, and it's very important that to prevent loss of life and destruction. And thus, also when a building goes under fire, in addition to the loss of property, it also impacts the environment in a big way with respect to the kind of flames that or carbon deposits start moving around the environment. Even if we are able to save the life, and that should be the first important factor. Saving a single life is the most important factor of a firefighting design. Do not consider that India is a very populous country. Losing life might be acceptable. No, not a single life should be lost, because that person whom we might lose with respect to not an adequate protection in the building could have been the future of the country. So that's very important that you as an architect should insist upon as you move forward in your professional career to have the best firefighting strategy in place before really getting into the other engineering aspects into it. And particularly for a tall building, I've just explained a little, the left-hand side has got its own, the building configuration, a building which is a mixed-use development. There's some shopping complex in between, then a mid-level of offices, and then a high level of offices. So this is just an example of a mixed-use occupancy building. So when you look at firefighting, you have basically two components. One is the passive component, and one is the active component. So the passive component is basically how you plan your escape route, the strategy, the placement of staircases. This is all been guided by the National Building Code of 2016, and it has been, like Gautam said, it is really well encompassed of all the experience of all the industry professional, and also international building codes have been taken care of. So the passive design is something that should be the first set of thought process which come from an architect. The active design is where an MEP engineer really does his job well. That means these are the mechanical equipments needed or the systems needed that will really push the protection of the building. So passive is something that would expect the architect along with the structure as well as the MEP engineer to all work together. But this should be your first primary goal of making the building, that it is passively protected, because it takes money for this element to be built and operate. But it is a one-time cost for the passive design. If you do your staircases well, if you do your egress routes well, and you're allowing people to escape within a certain stipulated time, you're going to save life. So do not compromise. Do not be under the pressure of any developer to tell me or to tell you that let's reduce the space of escapes. Let's give more carpet area. This is all fine. It is needed. But life safety is something is very, very important for you to concentrate while designing. What are the regulatory buildings? I've just given an example of a 126-meter tall building. Or for the information, anything in India in a 15-meter tall building, anything beyond 15 meter is called high rise. So that's how high rise is defined in India. So anything above 15 meter is called high rise. So the National Building Code has got its own standard for various kinds of building, various kind of occupancy, whether it's a hotel, whether it's a tall commercial, so various occupancies have their own perspective and compliance need. A building like this, just to give an example, is a mixed-use development, having a shopping complex, an office segment, and a high-rise office segment. And this being a commercial building of about 126 meters, I've just given what the internal elements was expected. So you need to have fire extinguishers, so that's a required point. You have hose reels. This is the firefighting zone that the firefighters use. And if you could see in your own tall buildings or where you can, or if somebody was staying or been going to some commercial building, you can see these hose reels being there, a red box which has got its own canvas connection connected to a riser. That's a requirement. There's a dry riser, which is basically if you have an external hydrant and if the municipal water supply is available 24/7, that's where you put a dry riser. And then the firefighting guys who come from outside, they plug the water into it and then they push the water to do the firefighting. But these kind of systems are not done much in India. It is done more in the Europe, where the central, you can say the town supply is available as a firefighting design. Wet risers is something that comes into within the building to connect to all your fire hydrant cabinets. Downcomer is again a part when the building is connected as a dry riser. So if you have a dry riser, you also have a downcomer connected to it. Again, not much in Indian context, but probably in the European side. Then a building needs to have provision of yard hydrant. So in the building design, you need to understand the perimeter of the building. And with every 30 meters, like assume you have a building line of maybe this is about 90 meters. So every 30 meters, you will have external yard hydrants. These yard hydrants are placed outside and it is a pressurized line connected to a sprinkler, a hose reel box, which is used to push the water from outside when there is an external fire happening. So the firefighters will use a yard hydrant and start fighting the fire from outside. And it's a very, very important safety requirement to be complied with. Then you have automatic sprinkler system. Most of the residential building at present at low rise, maybe up to 45 to 60 meters, do not have sprinklers within the building, but they have sprinklers in your common corridors or your lobby areas. But now it's a mandate across in terms that you need the residential rooms also to be within the coverage of the sprinklers. When it goes to mixed-use occupancy or a hotel, no matter whatever is your height of the building, you are expected to provide sprinkler as a complete coverage. So that's a necessity, and it covers the entire building. Manually operated fire alarm system. Fire alarm system gives you basically the signal if there is a fire within a space or within a zone. And it is required in common areas because people moving out, they understand that they can plug the manual call point, they can call your fire marshal, explain them there's a fire. And it's also necessary that we have automatic detection system. Automatic detection systems are your smoke detectors or heat detectors placed within occupied spaces. And these are addressable. That means they know that a particular flat and a particular room has got a fire and it has been, the signal goes back to the command center in the building. With this, it's very easy to fight the fire because you know where the specific location of that particular incident has happened to be. So that's something very critical for everyone to be knowing about. Some of the regulatory requirements in ventilation of the staircases, because staircases are something you should prefer to keep them outside on the building line, whether it is a tall building or not. If you keep them outside, it can easily be naturally ventilated, or once you start putting them within the core, it becomes mechanically ventilated. There are challenges. As a mechanical engineer, I would always say keep it as to the external periphery. But yes, you need to have the vision outside, so you will start building them inside. But once you start to build these staircases within the building, you need to mechanically ventilate it to keep them out of smoke. That's a big necessity. Tall buildings need refuge areas. I think I'll just give a little more example in the next slide of refuge areas. It needs a fire truck movement across the entire property. Generally about 7 meters to 9 meters is what the expected fire widths are around the building to be clear of any development. So if you have a building around it, you should have fire tender. The fire tender is the great red engine that you can see, the firefighting engine that comes. You might say it's about 4.5 meters, but what happens is it's got its own external jack, so it needs to hold themselves there and then fight the fire. So it's about 7 meters to 9 meters, and in some of the cities, particularly in Hyderabad, it has even got to 12 meters based on the building height. The width of the requirement is subjective to what kind of engine the municipality, fire municipality uses across. Some of the latest European fire engines coming through, they can even cater to about 120 meters directly from one point to one point. So it needs a bigger holding area. So sometimes the 7 meters goes to 9 to 12. I think nothing more than that. Then when you have basements, whether it's tall building or not, you need to compartmentalize the basement, because basement is the area where you have maximum amount of fire that can happen through, because your cars are your sort of an explosive zone. One car in terms of fire can generate 4 megawatt of heat, and that start of a fire can actually really take your entire building down in less than about 20 minutes. And then the requirements of pressurization. You need to pressurize the building either naturally or mechanically. So particularly in lift lobby zones where is a zone of your common movement, you need to pressurize your lift lobbies, your staircases and stuff like that. So this is just basics on the fire that you as a designer moving forward should concentrate on. So here I'm just explaining the same building in terms of how the staircases were been laid for. So this is the same building. You can see the section down below is the section that you can see here. Is my screen visible to all, right?
Yes, it's visible.
Sorry, I'm just going to act in between. Otherwise, I will feel that I'm just talking to non-existent zone. So it's very difficult. We have been doing kind of virtual interaction in a very difficult way. I think, so let's, if you feel that you're not able to gauge my points, please do let me stop me across. Okay, fair. So what we do is, I'm just taking you forward. If you can see the section that is below here, the lower section is what we are doing the analysis about. The green areas are where these staircases have been planned, and it is with respect to the design codes and National Building Code. You see the circles of the expected movement. The red lines are basically the movement of the people to get into the staircase code, and it has to be within a certain distance, maybe 45 meters if the building is sprinklered. That means if you've got an automatic sprinklered system building, then the staircases to the access from say last point to the section where I can enter the staircase should be within 45 meters. And so that's the reason why you need to plan for staircases as your basic prevention or egress route as your passive design. Same is the case for my floor typical above. If you see the typical set of floors, which is a lower footprint, we have 2 staircases that can work through. And then you have the access of people coming in, going into the staircase. So this is a very critical perspective that you need to design the staircases and the travel distance. So please be very careful when you get into building design, looking into planning the staircase and the travel distance. All been there in the National Building Code. What is the minimum it can take through? And you need to also design your staircase door width with respect to the number of people that's inside. There are calculations for the door width and the riser in terms of it can't be more than 150 mm. The steps can't be more than 150 mm. You can't give a 400 mm step and start hopping around in your escape. So it should be as smooth as possible in the movement of your egress when you need to work through this. So that's the intention of this planning the staircases. So this is what I explained to you about the means of egress. You need to add refuge areas. The refuge areas generally start from the 24 meter of a building. So the first refuge will start at 24 meter, and then every 15 meters you'll have your refuge coming in. So refuge is the space where it is more sort of a buffer area for the building occupants, because if you have a tall building, say 150, 100, 150, 200, 300, you can't reach down through your staircases. Your lifts are supposed to be non-functional during fire. So the lifts will go off, they will not have power. It will get only charged by the fire command officer, because that's an independent access only for the fire team. But as an individual or occupants on the building, you're not supposed to escape through any lift because you will not have power over there. You're supposed to go to the passive protected staircases that has been designed for the building. So, but when you start going from 100, 200, 300, it is not practical to reach to the bottom level. By that time, there will be various stages of fire. It can happen. You never know this. The most difficult fire is the one that happens the lowest floor, because the propagation from the low to the top level can be as fast as 30 seconds to 2 minutes. You know, that's how it can be. So you need to have buffer zones where people can be taking their rest. That zones are called your refuge area. Now, these refuge areas are planned in discussion with the building codes, National Building Code, and also from the fire officer. So the fire officer also indicates if you have an access of the fire engine across, then they look at from which angle they can save with respect to where the fire engine can be stopped and they can reach. It's not only the reach of the fire snorkel, but it is also the reach within the staircase for the firefighters to go and save this area. So generally these refuge areas are in and around your firefighting lobby spaces. There are some consideration for designing them. It's about 0.3 square meter per person, and there are some more technical perspective which I would suggest that if you can get hang of the National Building Code, please look into it. But I'll just explain a little calculation that for that typical building that we did. So we have the basements, the one which I explained to you, the building that I explained to you. There are 4 basements which has got car parking. Then at the top levels you got mercantile buildings. That means your shopping or retail segment. Then from 5th floor onwards, you have all offices. So it's in classification. So even this classification is been explained very clearly as per National Building Code. So the National Building Code explains what is the various classification that you should consider. Whichever is the stringent or most difficult classification is the design criteria for your building. So if you have a building which is purely office, you will not mind it. But if you have a building which has got a mixed use occupancy, you've got some residences also, then whichever is the stringent perspective should be considered. So assume that we have mercantile, which is supposed to be more stringent. So they have norms with respect to that. So what you've done at every 5th floor, that's how your refuge start comes in. Then every 15 meters from that refuge floor, you have the next set of refuge, next refuge, refuge, refuge. You can see the cross marks. And if you can see, I'll just zoom into this section there. The staircase which I explained to you, that's this zone where you have the refuge. So you can see the fire lift can also access these refuge areas, and it is under the control of the firefighting staff only. This lift gets activated during fire only by the fire officer, and the building lifts are always closed. So that's how they start evacuating. So positioning of this refuge area is the most critical design of how it needs to work through. So as I explained you may also have your fire tender movement all across. So you can also, with respect to the snorkel that your fire tender has, you can reach to certain level. In India, we don't have not more than 90 meters of the length of the snorkel. There are some cases being discussed that might get 120 meter fire engines in terms of snorkel length. But that's how the requirements are. So some examples of how the coverage is designed for what is the area consideration for that. So that's how we just work this. So this is a very basic but a very, very informed call you need to take during design of a building of a tall. Design your refuge spaces, design your staircases right, design your egress movement right, give them the width that is needed for moving, and then look at the MEP engineer to work out the other strategy, which is basically your Just to give an example, we also did a fire spread analysis on the tall building. I'll just run a small video. Not sure, it does not have sound, but it has got some visuals. It may not have clarity much. It may be having some pixelation, but I'll just run through this. And then I'll show you some of the, just advise me, Ajit, if you're able to see this.
Yes, the video screen is loading up.
So this is basically the mercantile floor at below, where we are assuming some fire to begin up. And then the fire moves to the core. The core is where my elevator's bank was. And you start looking at this is the simulation of the smoke. You look at my time elapsed. It's about 14 seconds. And you can just understand how the fire smoke spread. And smoke is the most critical element in a building that can kill. So this is a top view of that particular segment, just to see how the core is basically the elevator bank or the staircases section, how the fire smoke starts spreading across. So practically from 25-second onwards, you can see that the smoke has started moving into the zone. You have your fire walls, your rated walls to close them, but it will slowly start penetrating if there are even small leakages. That's the reason why you need to pressurize. We design a pressurization system. We also design an evacuation system of smoke. You can see the smoke coming out from the elevator banks, and that's how it will start traveling into the building top. So this is a demonstrative video worked out for a typical building to analyze how the smoke can move in, going through. And you can see the smoke is now started moving into the elevator core. And that's your most dangerous part, because once you reach your central core, which is your elevator or your staircases, it will travel right up to the building to the most easiest route. So like I explained to you, that the video that you saw was looking at the point where the central core is here. And if there's a fire, generally the maximum load, the fire load is a mercantile building, is a retail area, because you have apparels, you have something else. So you have a fire load which adds on to the problems there. So that adds up to the smoke spread getting within the central core. And just the same pictorials have just added up in the presentation, just if the video was not clear. Just going at 30 seconds, you can see how the smoke has spread within the core. The next 60, it has started going outside the building also. I mean, it's spread through. So I think there's a good question in between. Somebody was texting about what is the facade venting system. That probably Gautam and we can speak about during the question answer. You can see how the expected smoke is moving out. So if there is a window here, you open up, you allow them to move through, but it can also spill over. It can also, with the temperatures being very high, it can even decimate the glass, and it can get the glass will get destroyed, and the smoke can either move back to the building. These are some critical design that you need to really look into. Look at the factor that the central core where your staircases are, the smoke moves right into staircases or your elevator banks, and probably at 120 meters it starts penetrating the building. Once it starts penetrating building, your building is in trouble. It really cannot. So how do you really arrest it? You really start thinking the active components. That's the reason why this design, I would always say the passive is to be done in the concept design of the active component is when the building is all the measures of passive strategies. The active component, basically the equipments which we can douse the fire comes into picture. I'm coming back to the same discussion. The active component is the suppression system. After the detection comes in line. So detection is basically sprinklers, your smoke detectors, and alarms. So when the alarms has been generated, this suppression system will get the signal and they start working around. But let this not happen from the design side. Let the passive side be your first line of defense. Even when you look at fire engineers, they want your passive design to be the most important factor in a building to be considered. So this is some of the schematic that if I need to do an active component firefighting, so we do have water tanks in the basement, then we have a pumping system, and with various zones, as the building keeps on changing from say 100 meters to 200 meters to 300 meters, there are multi-stage pumps that we use. So we call it as zoning. We have a low zone, we have a mid zone, and we have a high zone, and that's how the pumping keeps on happening. and then your firefighting is continued with the sprinklers. So the challenges that I would request you all to just note this in your as a takeaway, key takeaway today would be to size those pumping. I mean, how do we size this pumping? The location of these risers, and because it's a top building, there are some pressure that it. There are some drenches needed for the facade. One of the questions that probably we can answer after this would be how do you contain the fire in the section of the facade by providing some. There is a water curtain designs in basement and parking area, again to prevent the smoke from moving out of the building, holding it there, and then we have extraction system. There are some evacuation system in some of the cities still in consideration. There are some lowering device, or you can say, now we can call it elevators or some fire chute, which allows the firemen to access and pull them down. Some pictorial representation of how the yard hydrant, external hydrant look like. So I think that's the main key on your fire. I have spent more time on fire because I believe that's the most important design aspect that an architect should consider in the future that you start building on the buildings. The next slides are going to be a few numbers only. The air conditioning of the building. I'll just explain a few basic parameters. I mean, what do we do with air conditioning? We control the temperature, we control the humidity, the air quality. It's very important that you should breathe good air, and we have to pressurize the air so that the air you are not taking from cross contamination zone to yours. Assuming that you've got some sort of a negative areas around your space, you should not get the air from the negative space to you. So assume you've got a garbage room adjacent to your flat. You should not have air coming from a garbage room to your flat. Your flat should have more pressurization to push the air out. It's very necessary because it's going to harm you in terms of getting these negative components. And then the smell. So practically all these put together is the process of what the air conditioning is all about. It's basically creating an environment where you can live, breathe, and be successful. There are some various different types of air conditioning system that we use. We have in commercial buildings, we have centralized design. You have generation at one point, start dividing it into various building clusters. Generally in residential buildings or in smaller offices, we have unitary. That means every floor or every room has its own small unit, either a water-cooled package or an air-cooled or a VRF unit. Your home, you might have split units, or you have the window units, something like that. That are all a part of the unitary component. We just explained, some amount of aspects of in terms of savings that we have. In a commercial building, as a good energy designing perspective, we should always look at designing on a central building. So it should be centrally air conditioned. So you generate your air conditioning at one point, deliver them through network of piping. That's how we take it forward. So that's the intent of being a centralized and a unitary concept. The tall building adds to the challenges in terms of the wind pressure and air. So the humidity at top levels are totally different than what you have at the bottom level. The air becomes very thin. It is less of oxygen. So people who live at the topmost level really cannot pull up their windows and assume that you can get good amount of oxygen or stuff. Really find some difficulty in breathing. So you need to create a design where the central ventilation system is able to work through. That's the intent of this slide, to explain the collaboration between the external environment and the building height. This is a typical case of an air movement. The air in a tall building, if you see an openable facade, which is generally accepted up to 100 to 150 meters or maybe even 200 meters. But if you go building beyond 200 to 300 or 400, 500, facade opening, I think even probably Gautam will later also add up. Opening up a facade is the biggest challenge. You cannot just open this because the wind pressure is so much. So when you cannot open it, you need to really pressurize the building in terms of air to come inside. So these are the spaces that you need to add if it's an enclosed property. If it's a lesser height building, maybe 100, 150, yes, you can have your openable facades working through for the air to move. And as your building goes taller and taller, the elevator shaft will go creating more amount of its stack effect. So pressurization, and like I said, if there is a fire here, the higher the taller the building, it is easier for it to find its space to go and reach the smoke across. So we need to pressurize this. These are the critical aspects that we need to look into the buildings on. If you really look at the challenges on the mechanical service, if you can note this, we need to look at the pressurization strategy, the stairwell, the staircases where you are exiting out, you need to look into it. Ventilation system design for a typical residential building. The kitchen exhaust, you have tall buildings and you have the small propeller fan sitting for this kitchen, and you see the wind pressure. You cannot exit the air from your kitchen spaces. So you need to design a facade which works with a pressure from the internal fan that it can push through, and it's not a propeller fan. You need to design a different system. Then you have a lobby pressurization system to keep the lobbies free of smoke. Very, very necessary. You have to push the air into the space. You need to design the mechanical ventilation of the heat rejection, whether it's VRF unit sitting at top levels or whether it is going to be unit sitting at the building top. You also need to look at the self shading and mutual shading of the building, because there will be tall buildings, they'll start shading each other. So you need a facade which needs certain amount of sunlight also to come in you to keep yourself or the daylight to come inside. And definitely the condensation analysis. As you start going taller, there are issues with this moisture that you need to manage, and with the wind pressure hitting onto it, you will start having condensation on the systems in high-rise building. So that's your gist on the AC services. I'm just running a little faster on this because I'd like to get some time with you all to interact. Something on the electrical. Most important factor on electrical is basically the transformers. You get a power from your supply company like Adani or Tata Power, and you step it down at your consumable voltage. What lines we get from outside is very high tension lines. You can't take it, they are not consumable at your socket points. So to make them work, you need to have transformers. The transformer is going to step down the voltage from your main supply company to the usable point. Transformers of two types, very important that you understand this. It's an oil type and a dry type. Oil type transformers, if I go to the next slide, is actually put outside the building. You can't. So it has been done for big campuses, big kind of designs where your multiple buildings are connected and you can put the transformers outside. But if you do not have a landscape area, you do not have your open spaces, then you are left with no option but to put a dry type transformer. Dry type transformers are put within the building but can't go below basement 1 height in terms of the National Building Code. You can't put an oil-cooled transformer inside a building, that is given, because it has explosion issues with it. So it needs a lot of coordination. If you want to put it inside, it can't have a basement. You have to create a lot of space. The expectation of putting the transformers are expected at ground floor, but at the worst case, you can put them in basement 1. So some type of the metering that we use in electrical is LT metering, HT metering, and hybrid. Now in residential buildings, LT metering means every power of your consumption, you got a small meter sitting at your meter room. HT metering, the metering is managed by your supply company. It could be Adani or Tata Power. It could be a single building owner where it is going to be hotel, occupant, commercial tower, or it can be multiple usage like malls and leasage. Then there is a combination in terms of HT and L3. When you go to tall buildings, you need to be doubly sure what kind of metering you need to work through. Because if you have metering at 1 floor below, that means if you're doing a residential building, assuming you have all the metering at one point, with respect to the supply company, they said, I need metering at all points. Assume you have 1,000 flats in the building. You have 1,000 meters to be planted in your ground floor. Giving a space for 1,000 meterings is another problem. And from there, imagine single cables going back to your building line, which is again a fire problem. So we need to interact with the supply company, and we have a solution we call as bus ducts. So we take one common bus duct and have metering at various segments. Maybe at every 7th floor, you have one cluster of meter. Next 7th floor, you have another cluster of meters. So this is the coordination that needs to come up with. So just an example of those metering, how they come. So you have a transformer that sits at the floor. Then you have these bus bars coming in. And at the section side, when I said, if you don't have bus bar, you need to cable. You see the amount of cable that will start go from bottom to top. This is a big fire hazard that you should consider when taking. Now, as your building really goes from tall to super tall, fortunately in India, you don't have these examples of putting transformers at, say, top levels, but definitely in data centers, we have the classic example of putting transformer even at 100 meters, that kind of design. But yes, if you see Burj Khalifa, there are about 4 zones where they had transformer. One being probably at the ground floor, then a midway, then a 3rd and 4th. Now, how to reach there is a logistical challenge. So we have to create all the movement space within the building to reach there also. That's how critical they are. And like I said, when we design the diesel generator, which is a backup for your powers, they are not allowed in any up. You place them at ground floor, or you place them at your the basements. So just to identify the challenges, another 5 more minutes from me in the big numbers. Distribution system, you need to take a call along with the engineer, along with the floor space that you're going to lose through, along with the supply company, that is your Adani or Tata in Mumbai particularly. Understanding of how do you distribute the electricity from use cables or you use a sandwich bus bar. Bars are basically, the entire power goes through a cubicle of 400 by 500 mm sort of it's just like a small column that moves from top, taking power along. Then you need to decide the metering strategy, whether I'll do it one point or whether we do it all floors. And then the earthing system with structural bonding, because the building needs earthing. It also needs lightning protection. So we need to design the facade to connect the facade with lightning protection as you go taller. And then we do the optimum transformer sizing. That's the key takeaway that goes in the challenges of the high-rise services. Now coming back to public health service, there are various ways of doing the building in terms of tall. You have small single booster. You can do it from bottom to top. You have a roof tank design that I pump the water from bottom to top, and then the top 3 floors will be provided with additional booster pressure, and then you have a gravity feed which can go and connect to all your residences. Or you have series connectivity. You have multiple pumps at various zones doing the pressure. What you need to know is that you need a minimum 1.5 kg of pressure, or can say 1.5 bar. 1.5 bar of pressure is needed for your shower. I mean, if you take a bath, you need the shower to have 1.5 kg pressure. 1.5 kg pressure means 15 meter of water column. That means if I need to have some, assume I need to have, I'm bathing in my topmost floor, my tank from which my water was to come should have been 15 meters above from my terrace level for me to get a sufficient pressure. That is practically not possible in design. That's the reason you have this kind of boosting system done. So you have small boosters to take care in the first top 3 floors. And then you have various other zones. You can divide it by small zone. You can do smaller intermediate tanks and do it. What we do is we do life cycle analysis or various system designs and then compare this. This is just a graphical representation of how water should flow. You have a multi-state design. It is feeding your next set of tanks, and then that next set of tank by gravity is taking care of some set of floors. Then the upper floors of that particular section is taken by an overhead tank. So these are basically some idea about how the water can be designed for in multi-storage buildings. So just a very simple, informative way of explaining you how water flows. You should try to do a design with gravity maximum, because not consume more power. In drainage design, we are now recommending for tall buildings to go with combined stack. That means you can combine your black and gray. Black water is basically the WC water that you come with. The gray water is basically all your water that comes from your shower, from your side, and all those things. So we can club them in terms of having a common riser. And more important is to design the riser for the adequate size, so that when the flow happens in the riser, it is allowing the venting also to happen. So that's something very critical as you look into. And then it's a requirement that you need to do the building with zero discharge now. What is zero discharge is? You need to compute the total water requirement, depending what is your domestic consumption. Domestic consumption is basically what you use for your human consumption in terms of cooking, bathing, and all those things. Flushing is the water that you use for your WCs. So you have 2 components coming for your domestic consumption and your flushing as your total water requirement. This water has to be mandatory treated by a sewage treatment plant. This is the necessity in any building which is now more than 50,000 square feet. So even in a residential building, it has become a mandatory that you need to provide sewage treatment plant. So this sewage treatment plant will receive the water from your usable spaces, and then it is treated, and that recycled water is going back to your cooling towers, flushing, landscape. That's the reason we call it zero liquid discharge. So we are not putting further stress on the system across in the municipal system. So that's how water balance is very important. Again, these are some of the challenges that we are looking at high-rise. So, I mean, drainage, venting stack, there are issues with pressure and gravity that need to work through. So we need to take care of the challenges of high-rise in terms of plumbing. It's and should be to absorb these shock loads of the networks. The last segment that I'm going to touch upon is basically the building segment. Like I said, the Chaukidar that you have is the intelligent Chaukidar that we do for building management. Building management system are basically intelligent microprocessor-based controllers, wherein various segments of the building operations electronically are plugged in together so that you can operate them at one point. Imagine a building at 300 meter tall. You have so many equipments at various places. Nobody can go on and switch them on and off on a regular basis. So you club them together into one common vertical communication system, whether it's your elevator, whether it's your air conditioning system, whether it's your plumbing system, whether it's your electrical system, or anything that you need to operate is in the building management bus. Even your fire alarm system, the notification of any fire, that's also on a common system. That's how you basically integrate the building management into one common solution. That's the kind of explanation I'm just adding. So you have HVAC control, the lighting control, the energy monitoring control, the motor control, the access control, the security, the critical power, all under one common software integration. It's an intelligent Chaukidar that we built for building, and for a campus, probably you can call it, but it does its own analysis. It's a data analysis that it does, and time program them when building should start, what should start, when should stop, and all those things. So you really can create these kind of graphic interfaces for the equipments to run. It's running through because there's a little too much on numbers over here. These are some of the interfaces that it looks like, and you can even create the graphic interface on your laptops to see what was the consumption of these particular, say, base building, what was the chill water plant consuming, how much energy did it take, all this kind of stuff you can make this look more interactive. You can understand in a month what was the consumption of power in the next month, or probably you see in a month, in particular in Mumbai, you can see May, June, July, you have higher energy consumption because your air conditioning systems are running at very high requirements. These are something that the building management system can do. So now let's sum it up. I mean, next 3 slides are simple, very simple. We'll give you a little more interaction. I'm summing this up. So if you want to do your space planning, this is something which I'm very passionate to talk about a few more minutes. Do I have 5 more minutes about this?
Yes, sir.
So I would request all of you to consider your building as like a human body. Very important that you treat the building as your human body. What you see outer, and I will add up with what Gautam was saying. Basically your skin is your facade, which you see that you have a good skin. But what is within your body is what the MEP system is driving the building to survive for. So if I compare with your brain, the Chaukidar that I told you is the building management system. It is the brain that is making the system to function in terms of running. So I'm comparing the brain with a building management system. You have a nervous system which connects your brain with the various organs that is connected to the body. Your nervous system is your electrical system because that's where my pulse, my feelers, my power is going to the property. The nose that we use to breathe is your air conditioning system for your fresh air management. So you connect that with your fresh air. The food intake that we have is basically the energy consumption that you use to run the building. It's very important that if you want to have a lean body, you will have less food intake. You need less energy consumption. If you're going to, bloat yourself, then you need more energy to work. That's how you need to design a building with proper thought process. The bones and the muscles, and I'm speaking on behalf of Girishji over here, are basically the structural elements. The one that holds your body. So whatever you have, the columns, the pillars are basically the structural component that holds the building well. The lungs, which is basically filtering the air that comes inside, is basically the air conditioning HVAC system. Like I said, it is taking care of humidity, it is taking care of your temperature, it is taking care of the air quality. That's your air conditioning system. Then our heart, which is pumping the blood to across, is basically the pumping system within the building for your chillers. We have sweat glands, we sweat. So whenever we do air conditioning, it is absorbing energy from one point, but it needs to dissipate somewhere else. That dissipation in a water cooled or central system is a cooling tower, which is placed somewhere. You can see some of these cooling towers in hotel buildings and big commercial. The kidney, which treats all our incoming fluid and then exits out with giving the other segments around it, is like the sewage treatment plant. Our intestine is like our organic waste converter. The excretory system is the power transmitter transformers that we use. You have various bloods and vein, which is basically the hydronic piping that connects the building, whether it's still water, water supply, drainage. And the foot where we stand on our property is the foundation. So if you can see, if you are passionate to design a building, be passionate about how you correlate that with a human. If you can cover up all this in your system, I think that's the best building that you can design with. I've just given some examples, just look and feel of the positioning of these equipments. If you see practically, this is the same building that I explained to you. Now I'll just go where and how things have been placed. So if you see at my lowest level in the commercial building, we place these air conditioning plant rooms, and you can see the huge mass volumes. You have 5 meter tall, 6 meter tall components. At segments that is at the topmost level, which is as per National Building Code, you need to have a fire water tanks. They should not go below basement 1. At your level 1 or ground, you should have your electrical substations and nothing lower than B1. So that's something that is very, very critical for you. At your endpoint, which is your domestic water tanks, can be below your fire pump room. The sewage treatment plant is something as per codes and as per municipal requirement has to be naturally ventilated, be placed not more than in 1 floor below. Then you can see in the distribution that if I generate electricity, I can have meter rooms at various floors, or it can have it per floor. So whatever air conditioning I'm generating is going within the building, catering to all the areas, and the heat that is assumed and occupied through the building has to be discharged through these cooling towers. You can see the cooling towers at the top of the building. And at the top of the building, you also need to have this overhead water tanks, which is connected to your underground water tanks. And that's how the circulation of the building really comes into. Similar case for a residential, everything else being same, the electrical being same. What you generally take out is you do not have these central plant units, but you need a breathing facade. So when your breathing facade comes in, you need these kind of outdoor units to put through. And otherwise, everything else in a commercial and residential is similar. But generally, the air conditioning systems are a little different in a residential building. But like I said, here in a tall building, 150, 200, 300 meters, you can't really put those split units to work. Because the back pressure of the wind is so much that it will do reverse work. So it doesn't work there. So split units don't work. You need to put this kind of outdoor VRFs. I think this is just a nutshell of which I thought I can pull back to you. So that's how things are. So I hope I could give you some insight of what MEP system are supposed to be. Yes.
Thank you, sir. Thank you for the wonderful presentation. In fact, the last illustration that showed the analogy of the human and the building function was beautiful, and we could kind of relate to it. And I'm sure students will relate to it while they're designing and the planning phase. So here we see that while designing, one cannot really plan in isolation. As we saw in the presentation here, there are several aspects that we need to often consider and address together, be it structural systems that we saw yesterday, the service core, the facade design. And by addressing all these systems together while planning, one can also avoid a lot of conflicts or the clashes that can arrive during the execution phase. So in today's presentation, that is the MEP systems. This is a system which normally turn the building from the empty rooms into a comfortable spaces that are more welcoming and livable. And there are 3 technical disciplines that really encompass the systems that allow the building interiors to be more suitable for the human use and occupancy. So thank you, sir. Thank you for this presentation. We will now go ahead and take some time for the questions and club both the questions, the previous speakers as well as this. So I request our moderator, Ms. Janisha, to kindly take the questions now. We have just 10 minutes to go.
Yeah, thank you, Shrutika, and thank you, sir. So we have a couple of questions from the students. Sakshi Motwani, are you here? Would you like to ask your question? So Sakshi had a question about the refuge areas. Are you here, Sakshi? She asks, are the refuge areas still provided after every 15 meters if the floor heights are larger than standard?
Yeah, so we said that I think after every 24 meter of the building is the first refuge that need to come through. And at every 15 meters, you need to add the refuge with respect to the floor plate. So there is a calculation on the floor plate and the occupancy. That's how you start getting them. So every 24 meter, your first refuge will come, then your next refuge will come at 15 meters and you add them.
Yes, all right. So I think her question was that if she has larger height of 5 meter of floor height, then it won't be feasible. But I guess that's the building code, so you can't do something about it.
Can I come in here?
Yes, Anuja, you can please.
Yeah. See, it is as per the bylaws, and always the refuge areas are provided for the above floor. So it's not a calculation for lower floors. Where you have it on the top, and the 2% of that is provided at the below floor. So ideally, whoever are the occupant from the top floor, they should egress towards the lower floor. So idea is that you are running towards the ground, and that's how the egress is happening. What the basic logic is, and all these calculations are elaborated. If you look at BMC bylaws, it is at every 24 meters. In unified DCR, it starts at 15 meters. And in NBC also, we'll talk about 15 meters because NBC says that beyond 15 meters, buildings are high rise. And unified DCR says 15 meters, they are special buildings. So that's how they are defined. So you have to refer to the bylaws, and accordingly, it needs to be. It doesn't have anything related with the floor to floor.
There's another question by student Ritika. So she's asking, by adding layers of fire resistance material in the walls and flooring and ceiling, how much will it help with fire resistance? How effective will it?
See, there is a calculation that is necessary. I mean, like I said, if you have a mixed use development, then you need to design the building for the larger fire resistance. So if you have a mercantile space below, that we have retail or shopping complex within the same mixed use development, then the fire rating would change with respect to maybe not 2 hours, it can become even 4 hours of that material component that needs to come in. So the core can get designed for your higher fire rating. So it has to be compliant to whatever is your stringent norm that need to come. But there is a minimum rating of minimum 2 hours for the cores. There are ratings for 4 hours for all the services spaces, like in your transformer room or your DG set sections. They all need to be of 4 hours rated. It is basically to hold any kind of fire load within inside. It doesn't spread out. So you are giving more time for the response. It is all depend on the response time needed for the building to get. So more taller the building, you need to give more response time for people to escape. So more stringent your fire design consideration should be. It also depends on where your fire, fire service station is nearby to your property, whether they can reach within 30 minutes, or it's going to be. If you're in Mumbai, you can't even think about any fire station to reach you in 30 minutes. So you need your building to be designed for minimum 1 hour in the water storage capacity, so that when my sprinkler system work, it is designed for minimum 1 hour. Anything above that is plus, but at least it gives you a ample time for people to fight the fire, get into spaces where they are safe. So fire rating is, again, like I said, it's a mixed design thought process should come from day one. You need to analyze the strategy of spread and then define between 2 to 4 hours. Nothing more than 2 to 4 hours is needed in a building for sure, in terms of space.
Aishwarya Matre, are you here? She had a question to ask. Would you like to ask your question, Aishwarya?
I've read something from Aishwarya rating. How is the maintenance of plumbing system work in high-rise building? Good challenge. First thing, you build the building right. Do not go for cheap materials. So taller the building, resilient materials have to be used. Materials which do not go by glue sticking, you go by fusion welding. These are the kind of specification that we specify in buildings that need to come. Because these the specification define the number of years that the system can survive. So a general plumbing system, a good specification, has got a lifespan between 20 to 25 years. Yes, post that you need those kind of replacement. But if you go for a cheaper building design, in 5 years, you will have a problem to go back and start servicing them. You need to take the pipes out. What fails in a building is basically these transmission pipes or transmission connectivity between services. So as a good set of consulting team that we have, we specify the client, we give them all the clarity that you build it to last for the building, the time that building can last. So replacing, like there's a question again from Aishwarya saying replacing old pipe with new ones. If you do a bad building, you will start replacing it every 3 years or 5 years. And with the kind of shaft spaces that unfortunately we get to work on, it is impossible to even get into the shaft space to replace the pipes. So, the planning in the initial phase is very, very important to decide whether you have space to even replace these. So you can't, in Europe, there are cases that people just build the pipe, put the pipes in the within the wall and forget it for 50 years. But that's not the kind of construction class that we are working in India, unfortunately. So we need spaces which needs to be accessible, serviced, but designed on the right front from day one. I think that's the kind of basics that we should follow. I think I've answered Aishwarya on those points.
Gautam, sir, we have a question for you from one of the students. They are keen on knowing about the kinetic facades, like what is the technology and what are your views about kinetic facades and their design?
Well, I think I'm a little bit of a purist if you ask me on a personal front. I find kinetic facades that actually consume energy to be a little gimmicky. That you're really trying to stand out by creating something dynamic on your building. So while there are certain technologies that actually are more clever use of kinetic technology where wind basically moves your facade. So, simple examples like, something that's really pivoted along a system where a plate of metal just moves with wind and that sort of creates a drama on your facade. That probably is a good way to approach it. While there are buildings that have sort of, done energy saving kinetic facade while trying to invest energy in running that kinetic facade, it's just, defeats the entire purpose of doing it in the first place. So I think trying to have some clever usage and then also seeing how much of energy are you saving and how much you're investing back into that system would be a good place to start. Also, what's important is to see the life cycle analysis of that, because there are complex components that break down all the time. If you have something that is screening your facade and it's fully screened your facade and it breaks down, which means you don't get daylight, you don't get views to the exterior. So I think those are very crucial decisions. And in my experience, all the complex kinetic facades that have arrived on the table have died down the design process because of those reasons.
All right. And finally, the question that was pending from the earlier session by Professor Mandar. How does the facade, I'll just repeat the question. How does the facade system operate at the detail level while addressing torsion, both directions, rotational sway, along with considerable lateral sway in vertical and horizontal direction? And detail, if that could be discussed.
Yeah, I will venture out into a quick detail share to sort of illustrate that. Can everyone see my screen?
Yes, sir.
Okay, so basically this little detail area that I'll walk you through very quickly is where all the magic happens. So this is a spandrel, this is a vision, that essentially is one full panel. And if I were to now the context is established, I'll just probably walk you through. So basically all the movement in a vertical frame, and this is a very project specific example. So if you can see that a vertical frame is split into two components which interlock into each other. So, any kind of lateral movements are dealt within this gap, this gap, and this gap here. So that allows both the panels to move independently. And as far as vertical stacking goes at the floor level, this component here is what we call a split transom. So the split transom also has movement capacity built in. So whether it's seismic, whether it's wind sway, whether it's sort of complex corner wind sway which lead to torsion, as Professor Mandar raised as a question, all of those have to be calculated. also seen how much movement capacity you need to build into the facade here, and these components are hence engineered accordingly. So I think the idea is that all of the facade that we see that appears to be very continuous, there are sort of visible breaks within that at every floor level and every panel level as well. So this component here and this component here is basically where all the magic happens.
All right, sir. We have a final question by Professor Parag, which I think is addressed to both Surat sir and Gautam sir. Could you highlight the precautions taken for fire safety and smoke seals in facade systems?
Surat bhai, you want to go first?
Yeah, sure, why not? I mean, as an MEP engineer, we provide the the mechanical elements in the building per se. I mean, there are smoke ventilation, smoke vents, or you can say pressurization system is something that we first consider, and there are also smoke extraction system on properties that we design for in tall buildings. But what is also necessary that there are codes now to be mandated at certain amount of percentage louvers that are or openable windows that needs to go on the facade in terms of either escaping the smoke to come out or even for the fire fighters to even access those areas. So in very high-end buildings, we also correlate these openable windows to some fire alarm system, which has got some sort of a link. So this fire alarm system is triggered when there is some sort of a detection in that area. So you get a power supply to that and the louver opens up. The louver opening up is the design for the smoke to vent out. So that's the kind of strategy that comes in. And probably Gautam, you can add up, among some of the details that you feel.
Yeah, so I think just to add to what Surbhai said, it's basically there are a lot of active systems to make sure the smoke gets extracted. You maintain pressurization in critical spaces. The role of facade is basically to make sure there is sufficient fire resistance available in the system, and then there is sufficient separation available between zones and between floors so the fire doesn't propagate from floor to floor. I think we have a few.
Anand sir has got some question. Yes, sir, please.
Sir, Surat sir, just your opinion on this, which might help probably to rethink certain guidelines. From the term of efficiency, when I see from the angle of efficiency, how do you see certain guidelines stopping you, as you mentioned certain points in your presentation, which stops you from decentralizing over centralizing? Like the one you mentioned on DGs are not allowed. But many situations where internationally adapted service flows, a lot of decentralizing services become more efficient.
Right.
But certain guidelines are not. So could you throw more points which are those which you feel from your expertise that these probably would have been better to have decentralized, but certain things have to be centralized? So your opinion.
Yeah. So when we really look into buildings, we design with respect to the loss of transmission. If the transmission loss are within the limited period, within the limited range, like in electrical systems, there is a expected range of less than 5% of voltage in the property. So when you become to really tall buildings, and if you can see the example when I started earlier with Burj Khalifa as an 828-meter tall building, it is not that it's got transformers only in the basement or ground floor. It has got transformers at the mid-level based on the load centers of the property. Now, when we design, it is dependent on the load center of the property. So where are the load centers? Generally, the load centers in a commercial building, if I example, is basically the amount of power that consumes within the core. There are your elevators, your air conditioning system. So, and where do the power for these core comes? So probably in the elevator system, we give them the power at the bottom. So there is a panel we provide for the elevators at one point. So the decision of decentralizing is also subjective to what the distribution strategy comes in. Now we have a challenge here in Indian perspective is, unfortunately, this service and maintainability at various levels are not possible. So you need to take a decision at what point you can service them, because if you have equipments at various floors, they need to be taken out also for the number of years of its working and the kind of size it needs to have. So if you start putting them everything at top or everything midway, you may need to create such a big hoistway like a car elevator to even go and service them back, if you want to remove some of these equipment. So decentralizing has got, particularly it's better to decentralize, say, plumbing systems, because it is easier to maintain the building in terms of the pressure, in terms of the hydraulics that we can work. But we can always centralize. Centralizing the major power consumption point is something that we always say put at one zone of the building. So like if you're taking an air conditioning plant room, it should be placed as close to your transformers, because the generation of the power is from the transformer to the plant. So club them, the energy center should be clubbed as close to the possible. But when you come to the residential segment, the power center keep on changing, because then it becomes every floor, every unit as its own zone. So when you come to really a residential segment, decentralized becomes your decision factor. But when it comes to commercial building, your centralized becomes your governing factor in terms of the space usage and in terms of the distribution cost. I think we'll have to bifurcate within the usage perspective and take into guidance the fact that the local authorities, how do they approve a certain, there are limitations in which the local authorities will not come within your building. They say, I have an access at only this point. I will only come within the property within a certain limit. They will not go within your building line to take your readings on the property. So I think that's also a very critical decision factor when the type of the building is under design.
Sir, my question was also with very specific point where efficiency comes into the picture. Like you said, today power meter meeting, as you said, nowadays there are technologies where a person need not even come to the meter room to take the reading with RFIDs and others. They're able to take it from a distance. So probably certain guidelines needs to be also relooked from certain things where it can shift from its position. So if we are talking about air conditioning, would that be central chiller plants would be still efficient? Yes, as you said, accessibility and serviceability should be there. But if there are certain minor space dedicated for service car lifts and others, would efficiency not increase in air conditioning if decentralized?
So again, like we said, sir, it again distributes in with respect to the buildings. Like my experience in the projects in, say, Middle East, I've done a tall building over 365 meter tall. But what we do is generating at one point in distribution. The distribution cost on an air conditioning system is not that heavy with respect to what the distribution cost on electrical system can be. So what we do is, when your bulk consumption happens, you put the power at one point, you generate your air conditioning at one point and start distributing it. So there is a trade-off between the source of generation and the pumping cost. And what happens in an air conditioning central plant system, it's a closed loop. So practically the pumping cost is not based on the building height, it is just the friction loss on the piping that we work on. So the friction loss is not really that expensive that my pump horsepower can change from 5 to 20 to 30%. What it needs is to be looked into is the hydraulics of the property. There are certain hydraulics on the property which equipment cannot take, because there are certain casing pressure that the building cannot take. Now, like I said, if I do a tall building of 200, 300 meter, I will break the pressure at certain point because I need valves to hold them. The valves in this industry in India perspective are not that too heavy that they can take the building heights. So we do break the pressures at certain point. But as an efficient design, if you're doing a commercial building, keep the load centers as close to each other so that your distribution cost becomes, electrical distribution cost becomes much more simpler. And then start thinking about breaking particularly the hydraulics in terms of the pressure. And I think that way, it's a win-win situation. What happens, unfortunately, Professor, is we really don't get that kind of heights on a building. There are restrictions of height when you come into design, but there are necessities of certain service floor. Unfortunately, in India, the service floor heights are given at 1.8. In 1.8 meters, you can't put anything in the design standards that we have to put equipment. Any equipment that really goes at certain level needs minimum 4.5 meters for them to be serviced, for them to work. So with limitations and design consideration, I think centralization of commercial building is a better option, and decentralization in residential buildings are solutions.
Great. Thank you.
Thank you.
Thank you, sir. Good question. Thank you very much.
Thank you, sir. We have a lot more questions, but unfortunately, we are out of time. So I hope you don't mind if the students reach out to you over email or something and ask you all
No,
their doubts.
that's the prime reason I in my frontal slide, put up my email address. Please do question this. These are all inputs that as a consulting engineers we always like to be questioned about.
Thank you very much, sir, for your time and your valuable inputs.
Our pleasure, my pleasure to be invited to such a distinguished team.
Thank you, sir.
Thank you, sir. So on behalf of WESCO, we would like to thank you, Suraj sir, for your time, and we would like to present you a memento.
My honor. Thank you so much. Wonderful. Thank you, Professor Anand. It was really very interactive. I'm very happy to get some questions which are really interactive. I think this has been one of my most interactive zones of presentations. You got a very inquisitive set of students with you. Very nice.
So we will hope we might take your help in the regular studio as the studio proceeds further. Probably we'll have some kind of program worked out where a few of the involvements would speakers we will take their involvement.
I'll be more than happy to be a part of it.
Thank you.
Hi, Suraj. Thanks, Suraj.
Thank you, Anuja. I think my friend has joined for sustainability, or is it later?
Yes.
What time is it?
Ankur is here. Ankur
Ankur
is
is
here.
here?
Yeah.
Okay.
There's Ankur. Hi.
Hi, Suraj.
Ankur,
Listen to your talk.
Yeah. I would have loved to stay back, but I've been getting quite a number of calls to attend, which is unfortunately I need to push out. I would have loved to be back with you. So,
So it's a
pardon me for that.
spectral day. It's a spectral days long journey.
We go
Right?
long way. Long
Yeah.
way. We all started our career together, so we're all grown together. Okay, Ankur, I know you'll do the best in your sustainability side with the team that we have here. I've just put some prefaces what the best I can do.
Thank you.
Thank you, Ankur.
So,
Thank you, sir. Thank you, everybody. Thank you, Anuja.
Thank you all. So we'll be taking a break for 5 minutes before we start with the next presentation. So I request all the students to kindly stay here and just keep your cameras off for 5 minutes, and we'll be starting.
We'll let them all come back by 11:15.
11:15. Yes, 11:15. Thank you.
Hello, Ankur sir, you have joined, I think. Is there? I think he's also put it on mute. Ajit has raised his hand. Shrutika, kya hua?
Yeah, I had a question, but never mind.
About?
In the question answer session.
Sir, about the facade, about the curved facade, Ajit sir had put the question.
Jinisha,
I request the class coordinators to just check with the classes if they're back. We can start with the next session. I think let's start with the next session. Otherwise, we'll be running behind the schedule. So I welcome everyone back. I hope everyone is sufficiently energized for the next session. We have with us our next speaker, architect Ankur Sangvi from Amas Architects, and he will be presenting on the topic sustainability in high-rise buildings and wellness. Ankur Sangvi has 17 years of professional work experience. He has worked on several projects from CII Sorabji Godrej Green Business Center to projects such as Bombay Dyeing, Axis Bank Building, Noida, Mumbai, Rajiv Gandhi International Terminal in Hyderabad. He is a member of the National Building Code Committee for development of a new Chapter 11 on sustainability. He is the member and member of the Technical Core Committee for IGBC Green Homes, IGBC Green Campus, IGBC Green Interiors, and IGBC Green Factory Rating Systems. He is a LEED certified trainer, and he has conducted several training workshops across the country. We welcome you, sir. Over to you.
Thank you. Can you all see my presentation?
Yes, sir.
Okay.
Yes, sir. Can you put it on full screen mode?
Yeah, I put it on full screen mode.
No, I'm not able to see the full screen.
Can you see it now?
No, sir. I think you'll have to share entire screen rather than
Okay, I'll do
share
that.
a window.
I'll do that. I'm sorry, I think, can you hear me now?
Yes, sir. We're able to hear you.
Yeah, I can't share the entire screen, it seems. There's some.
That's the first option in
Yeah,
present.
no, whenever I do that, the Google Meet crashes.
So press F5. If you could press F5.
Okay, can you see that?
No, I think we are still seeing the edit mode.
So still seeing that more.
So should we share the screen otherwise?
Yeah, if you could share the screen, that would be fine. Only thing is I'll have to keep saying next to you.
Yeah. Ajit,
Sir, can you share the data with me?
it's in your email.
Are we ready to go?
Yes, sir.
Okay. Sorry about that.
Is it okay to control?
Sorry?
Just confirming from Ajit.
Yes, I can control.
Yeah. It's
Are you good to go?
yes, sir.
Yes, sir, please start.
Okay. First of all, I'm sorry about the glitch. After a wonderful presentation by both Gautam and Suraj earlier in the day today, and one of the takeaways for me from their presentation was that tall buildings are very energy intensive, and calling them sustainable is actually a bit of an oxymoron because they are not actually sustainable, they are energy guzzlers. If you could just move to the next slide. But the fact is that in time to come, the way our population is growing, and even if you have seen Dheeraj's presentation yesterday, we expect to have 70% of our population living in urban centers probably by about the next 10 years. And when you have so many people living in urban centers, you're bound to have tall buildings. So you cannot escape having tall buildings. So the idea over here is to make sure that if we do have to go in for tall buildings, these tall buildings are actually sustainable. Next. When we talk about sustainability in tall buildings, you have to mention the name of Dr. Ken Young. He's an architect based out of Kuala Lumpur, and he was one of the first advocates of what he called the tropical skyscraper. And in 1980s, he actually postulated that you can have, glass buildings or the skylines that you have in New York and in San Francisco only in the cold weather that you actually have over there. And when you design for the tropics, the buildings have to be designed differently. And here, he actually talks about how, you need to have certain amount of shading devices, how you need to actually have, pockets of shade, you need to control the daylight. While in New York or in San Francisco, you want to have maximum daylight so that you can have a certain amount of passive heating over there. The energy loads are very different that we have in the tropics from what you have in the Western world. And he was one of the first persons to talk about this. Next. And this, of course, is his very famous, iconic Menara Messiniaga building, which is now the IBM Tower in Kuala Lumpur. And if you see the way this beautiful building has actually been designed, you actually have sky courts which act as shading devices, which act as buffers. You, instead of seeing a flat glass facade, you actually have a lot of areas which are opaque. You have a lot of areas where you have reflectors which reflect light deeper into the building. Next. Besides the IBM building, he has also designed a lot of buildings, where he then started talking about, rethinking the environmental filter. And if you see the building that he has designed in Southeast Asia, you have a lot of landscapes that seem to be spiraling into the sky, which seem to be acting as like a buffer, which seem to be acting like a filter against the vagaries of the environment. So they act as a filter against the sun. They actually act as a filter against the hot breezes that you have over there. Next. This is another building designed by Voha Architects, where this hotel has a live facade, as they call it. And this facade actually acts like a filter. It pre-cools the outside, the immediate microclimate outside the building, outside the facade. And it makes sure that the delta T that you have between the inside and the outside is not too great, so that you do not have a lot of heat ingress that happens through the facade. But one of the I won't say a criticism, but one of the things being said about all of these buildings is that, they may look like a green building, they may look like a building which has got a lot of vegetation, but does it really perform in terms of energy? Next. So, here what we have done is that we are actually working along with Anuja's office on a project. And I'm just going to show a few simulations that we have done for this particular project. Next. What we first did is we just analyzed that what is the conventional energy consumption of a building in Mumbai. So typically, you have a building which is consuming a tall building. It consumes about 32 kilowatt hours per square foot per year. Then you have a ASHRAE or an ECBC base case, which is supposed to be your baseline model, the minimum efficiency that is required for a building in India now. So that would come to about 27 kilowatt hours per square foot per year. And this project that we are designing, we are aiming to bring it down from 32 to 17. So what we are trying to do is we are actually trying to see if we can cut our energy consumption vis-a-vis a conventional building by almost 50%. Okay. So there are a series of studies that we did. Could I have the next slide, please? Where what we did is we did an analysis of where the building is consuming energy. So the majority of your energy consumption in a building comes from cooling. Mumbai is one of the most difficult climates to design a tall building in. And one of the reasons is that in Mumbai, you have the best views towards the sea, and your sea is on the west. So, most architects tend to design the western facade is a full glass facade. Now, the western facade is also the facade which has maximum amount of heat gain that comes in from the windows. So here we have actually a tough time in telling the designers and even telling the project owners that they need to cut down the amount of glazing that they have on the western surface. So we need to actually work out a fine balance, between views and daylight and the heat gain that happens, through the windows. A further analysis actually shows that, of the cooling load, if you see, almost 35 to 40% of our load comes in only from, the solar heat gain that comes in from the windows. So about 20% is equipment, 12% is, lighting. Actually, for every 1 watt of artificial lighting that you have switched on, you need to cool it down. So your cooling load increases for every 1 watt of lighting, it increases by almost 0.2 watts of air conditioning energy that is required to cool down the space. So these two are intrinsically linked. And then, of course, you have the different building elements. So you have window solar, you have, the conduction that happens from the window. So actually, windows contribute to almost 50% of the cooling load that you have in a building. Next. So what we have done is we have actually divided our approach into 2 parts. One is what we call the design approach. These are the interventions that designers can actually make to ensure that you have a higher level of sustainability, you have a lower energy consumption, which is basically your orientation and form, the envelope optimization, daylighting, shading design, ventilation design, and then you have alternate strategies. Next. So what we did is we actually took a baseline case instead of taking it as 32 because it was going in for ECBC. We said that your baseline building is going to consume 27 kilowatt hours per square foot. Now using orientation, using good insulated walls, going in for double glazing, we have actually gone in for triple glazing at places. We are actually able to reduce it from 27 to 26.5 to 24. Ultimately, from 27, we have a reduction of almost 12% just by good design, good architectural design. So we have brought it down from 27 to 23. Next. Then you have the equipment efficiency part, the equipment that Suraj was talking about earlier. When you're going for high efficiency chillers, you're going for either a VRF unit or you're going for water-cooled chillers, going for LED lighting, you're going for variable frequency drives, going for sensor-based ventilation. all of these things can combine, bring down the load further. Next. So there we started off at 12%, and from 12% we have actually reached up to a reduction of almost 42%. So from 27 we have gone down to 15.6 kilowatt hours per square foot per year. That is what we are planning to. Our target initially was 17. This is by going in for very efficient daylighting. Lighting design. Your typical lighting is at about 1 watts per square foot, but in this particular building, we are designing the lighting at 0.57 watts per square foot. So the amount of lighting that is required for the building is almost half. And if you remember what I said earlier, for every 1 watt of lighting energy that you save, you also save about 0.2 watts of cooling energy. So there's significant savings over here. And then you have going in for very efficient chillers, you go in for VFDs, you go in for something which is called demand control ventilation. You know, Suraj earlier talked about making sure that you have a certain amount of outside air that comes into the building. Now, what happens is that when MEP designers are designing your outside air system, they are designing it for peak load. Say you have an open office which is likely to have a peak capacity of say 200 people. So the ventilation system is designed for 200 people. But on any given day, say you only have 75 people over there. So you actually have CO2 sensors which sense the amount of CO2 that you have in your return air, and they modulate the fresh air damper so that you do not pay an energy penalty, so that you do not pull a higher volume of air from say 36 degrees to 21 degrees. So that is what is demand control ventilation. And with this, we have a certain amount of savings in the overall performance. Next. But sustainability is not just about energy efficiency, it is also about water efficiency. In fact, in the last couple of years in our country, what we have found is that energy we may be able to generate more, we may be able to cope up with higher energy use. But water is what is going to be a major issue in time to come. So there are certain water efficiency strategies that we are going to incorporate in this building. So typically, it goes by the same formula, which is your reduce, reuse, recycle. So make sure that all the WC, the dual flushes. You have faucets which have aerators, and what these aerators do is they mix air with water. So you actually get the feeling that you have a high water flow, but because it is mixed with air, the amount of water which is consumed is almost 30% lower. So you reduce the water consumption, and whatever water is consumed, you put it through a sewage treatment plant, and then try to reuse that treated water for either landscape irrigation or for flushing or for cooling towers if you are going in for water-cooled air conditioning system. So there's a typical water balance which is achieved by using a STP and reusing the treated water. What we have found is that typically in an office building, if a person requires about 45 liters per person per day, with a good STP and a good water reuse strategy, we can reduce the water demand by almost 50%. So a green building or a sustainable building will actually end up using water which is 50%, so which is about 20 to 22 liters per person per day only. And of course, Suraj also talked about zero discharge systems. So going in for rainwater harvesting, is one of the harvested rainwater is one of the cleanest sources of water, and there's an opportunity in actually harvesting that water. Next. Suraj also talked about in his presentation, he talked about IBMS system, and he talked about the Chowkidar. I'll take the Chowkidar analogy a step further. Actually, if you meter the amount of energy or water which is being consumed, then you are more likely to actually control the usage. One very interesting case study that we found was there's a project that we worked on, and they had a very good IBMS system. and it actually gave a display of what was the amount of energy and water being consumed immediately. So the building owners had put up this screen in the lift lobby, and all the occupants of that building, of that office building, could actually see what is the amount of energy being consumed. So what they actually were doing was they were switching off lights when they leave their workstation. They would switch off the monitor when they leave their workstation, just to see how much of an impact they are actually having in your energy consumption, because they could see it real time. Then they started tweaking with the air conditioning system. Instead of putting the set point at 21, they decided to see if they were comfortable at 23. And when they put it at 23, they saw a certain amount of savings. Ultimately, when you go to that building now, it is such a beautifully balanced building. Typically, if it is 21 degrees, you really feel cold sometimes when you enter into a building, when you're walking in from, an outside temperature of 36 or 40 degrees. So here you do not get the thermal shock when you get into the building. Plus, the metering and your real time seeing the consumption has actually produced a behavioral change in the users, which has resulted in at least a 10% savings in their actual energy use. So they've done nothing. They've not done any further investment except for putting the numbers in front of the people where they can see it, and that is actually what has saved a lot of energy. Next. Now, from 2001 till probably up to 2015, whenever people talked about sustainability, and I've very deliberately not put up the definition of sustainability in my presentation, because if you look at your classical definition of sustainability, using minimum resources to meet your needs of today without compromising the resources available to the people for the future. This used to be the definition of sustainability. But now what has happened is that people have stopped looking only at the planet. And there has been this change. That instead of looking only at, what is happening to the planet, if you could go to the next slide. Now it has become people, planet, and profit, where the people come first, where the end users come first, where the occupants come first. Then you have the planet, and then you have the profit. The thinking is actually this people, planet, profit is a tagline which is probably some 15, 20 years old. But now it is coming to the forefront because people have started realizing that we need to live in the present and not just in the future. So there's been a significant change. Next. So what has happened is that now you have this whole thing called wellness, which has been attached to energy and water saving. So now you have sustainability equals wellness, it equals energy and water. So when you talk about wellness, what is wellness? The practice of architecture that relies on the art and science of designing built environments. It's socially conscious systems and materials to promote. Basically, it is just talking about how you need to use the resources and how you need to use, the building design in such a way that it impacts the people positively first. And then we talk about, what is the impact on the environment and what is the profitability or what is the capital cost of going in for wellness. So this has been a significant shift that we are seeing now. Next. So what are the factors that actually define health and well-being? So one is, there's a need to go in for glare-free daylight, then you have clean water, you have fresh air, thermal comfort, access to nature, and the last one, which is most significant, which is community connectivity. Next. See, when we talk about daylighting, what happens is that, there's a certain definition of daylight. And when you have overlit spaces, people tend to actually pull down curtains and then they switch on lights. Or you have daylight designed in such a way that, you have daylighting which is reaching deep into your building. But people who are sitting along the periphery actually have so much glare on their screens that they can't work. So again, the same thing happens that, they are either uncomfortable or they need to, change the way they sit or they need to pull down the blinds. So when we talk about daylighting, it's not daylighting per se, but actually need to go in for glare-free daylighting for the health and well-being. Next. So when we talk about daylighting, what are the different factors? So I'm just not going to talk about daylighting. I'm also going to get into artificial lighting design as well over here. So the first is ensure that there is sufficient daylight. For a wellness certified building, what is typically done is that a lighting daylight simulation is done to make sure that at least 40 to 50% of the spaces have daylight which is available, which is between 200 and 2000 lux. Here it's not just a minimum number, but also a maximum number is given. Because anything which is more than 2000 lux is considered to be glare. So you need to have daylight between 200 and 2000 lux for at least 50% of the spaces of the time of the year when you have daylighting available. The other thing is that, how deep does your daylight penetrate? Typically, your daylight penetration is 2 times the height of your window. So say if your window is 3 meters tall, then your daylight penetration would be 6 meters. So actually the depth of a building bay is, an ideal depth is somewhere between 12 to 15 meters. So that you actually have more than 75 to 80% of your building which would be daylit. Similarly, what is also required is that we have often seen that, we have designed a daylit building, but then the interior designer has come in and has designed partitions which are opaque. So, the basic purpose of having good daylighting is lost. So here the important thing is to ensure that all the partitions that you have are, transparent above 42 inches. 42 inches is actually the height of, the line of sight of a seated person. So that is where this 42 inches number comes in. Also, if you go in for task lighting, what task lighting does is it delivers the actual amount of lighting that is required to the tabletop. And say, for example, you need about 300 lux to perform a basic task. So task lights deliver the 300 lux to your tabletop. But to walk and to move around in the aisles, you do not need more than 100 to 150 lux. So instead of actually designing the whole office for 300 lux, if you design the aisles and the walkways for 150 lux and only the tabletops for 300 lux, then you are going in for efficiency. That is how we have actually been able to reduce the lighting consumption from 1 watt per square foot to about 0.57 watts per square foot in the design that I showed earlier. The next is circadian lighting. Now, this is a concept which people are not generally very familiar with. So the human body does not perceive lighting as a static amount of light or a static color of light. So a human mind needs to see different temperatures, color temperatures of lighting throughout the day. So say, you have your yellow light, which is say about 3000 kelvins to about pure white, which is 6000 kelvins. So depending on the time of the day, you actually need to have those smart lights which modulate the color temperature so that, this adds to the occupant comfort. You are actually working in an area where you have lighting, which, is appropriate according to the time of the day. Next, please. Some buildings that I would like to show over here. The building on the right and the top left is one of my favorite buildings, which I studied as a part of my master's thesis. This is a Phoenix public library building in Arizona in the US, designed by Will Bruder. And this building has been designed in such a beautiful way. You have all these sails in the south, which make sure that you never ever have any direct lighting which comes inside the library. You always have indirect lighting that comes in. If you see the photograph on the top left, what you will see is that there's even distributed lighting. But this lighting keeps changing, throughout the day. So the lighting is not static. And what the designer has actually done is, if you see those columns, the columns don't hit the roof. You actually have a small circular skylight at the top. And these columns actually act like sundials. So you can actually feel the time of the day just by the shadow that you see on the floor. It's been beautifully designed. On the lower left, of course, you have the very famous Institute of Arab Studies, where the jalis have been used, and these jalis have been used in such a way that again you have a very dynamic character to daylight that you have in the building just because of the way they have been used. Next, please. Earlier we were talking about water conservation. While water conservation is important, what is very, very important in our country is access to clean potable water, which is very difficult for a large percentage of the population. Next. A wellness certified building typically requires that all the water that is, given in the the tap is used for drinking is actually filtered. And there are certain minimum specifications that have been given on what should be the pore size of the totally suspended solids. It has to be UV disinfected, and it has to meet certain minimum standards, so that the people, the occupants, when they drink the water, they are drinking potable and pure water. Whatever water is supplied to the building always has a certain amount of sediments. And here too, a well-certified building requires that the water be stored in a tank, the sediments be allowed them to sort of settle down, and only then that pure water from the top is used for any other purpose, which could be including flushing or even for hand wash. And the most important, of course, is that the water which is used in the building is tested, and the quality of water is actually displayed. You actually display what is the quality of water the end user is getting. That leads to a greater sense of well-being. Next. Access to fresh air is again one very important sort of a component of wellness. Next. So there are three parts to it over here. One is increase the indoor air supply, and there's a certain minimum standard where we typically have outside air that comes in at about 15 CFM. And if you increase this by 30%, you're bringing in more fresh air that comes in from outside. It leads to a healthier environment. And what also happens is that if you have more amount of outside air coming in, you are paying an energy penalty. So actually you go in for demand control ventilation that I described earlier, where CO2 sensors are used to modulate the amount of fresh air coming in based on the CO2 concentrations inside. The second is that you monitor the indoor air quality and see what is the CO2 concentration, and also what is the concentration of PM 2.5 and PM 10 particles. About a couple of years back, when Delhi went through a very bad phase of air quality in winters, we had seen a very, very high demand for people going in for green buildings and going in for well buildings, just because they wanted to assure their occupants that they are getting air which is of reasonable quality. Delhi, of course, is notorious for having a very poor quality of air. Next. So besides the ventilation, the other things that need to be made sure is that there are adhesives and sealants which carry a certain amount of VOC. There was this very, very famous Shah Rukh Khan ad. I think it was for Nerolac paints, where he actually said that ये वाली paint जो है उसमें खुशबू आती है, बदबू नहीं आती है. So what the manufacturers were trying to promote is that their paint is VOC free, and that is why it is not harmful to the human health. Similarly, you have certain adhesives, you have coatings, and also one of the biggest sources of contamination is composite wood. You must have heard that there are three grades of plywood. One is your typical commercial plywood, then you have what is called the moisture resistant grade, and then you have boiling waterproof grade. What actually happens with these three different grades is that the first is having urea formaldehyde as a bonding agent. Have you ever stood in a room where a carpenter is cutting commercial ply? It really smells so bad you can't stand over there. And it is very, very harmful to the health of the occupant as well as of the carpenter who's cutting that composite wood, who's cutting that plywood. Then you have your MR grade wood, which has melamine formaldehyde, which is not as bad. And of course, you have this phenol formaldehyde bonded. We used to have those kit ply ads. I don't know if you remember, where they said, "Hamara wala plywood to phenol bonded hai," which is a plywood which contains the least amount of VOC. So these VOCs tend to stay inside the room for a long, long time, and they are invisible health hazard to the occupants. So they impact your human health significantly. Now the other factor is ventilation effectiveness. So how you have your air distribution is very, very important as well. And generally what happens is that we have air which comes in from your top and is again taken away from the top. But that is not ideal when you are cooling, because cold air is heavier and you need to actually force the air at a certain air speed. Now what happens is that people who are sitting in the line of your airflow are uncomfortable, and people who are sitting further away need that airflow for cooling. So you have cold spots and you have hot spots within the same room. If your ventilation system is not designed effectively. One of the best ventilation system design that you can have is if you actually go in for what is called underfloor displacement ventilation, where you actually have a false floor and you have cold air which is circulated through the false floor, and you have small diffusers. And through these diffusers, you have air which comes in at very low speed and slowly, cools down, because again, air is stratified. So it slowly cools down the lower 6 feet of the room, so that, you only have that coolness where, the people are standing. And when you go higher up, it starts getting warmer. So not only is it a very effective ventilation strategy, but it is also energy saving. Entryway systems are again very significant, because we tend to carry a lot of muck in the shoes, which we wear, and when you walk into a building. And if you have a entryway system like a 3M carpet or like those gratings, what they do is that they actually track the contaminants and make sure that you do not have, especially you do not have smaller particles like the 2.5 ppm particles, which actually tend to stay within the air inside the room for a long, long time. So the idea is to go in for a revolving door, or go in for a carpeting system, or go in for both, which traps and removes the contaminants from people's shoes before they walk in. What COVID has taught us is that we need to have some sort of a treatment of your outside air to decontaminate it. And UV lights have become very, very popular now. So UV lamps are typically used on cooling coil surfaces. Two things, they serve two purposes. One, they make sure that there is no fungal growth on the cooling coils. And also what they do is that whatever air is pumped into the room is actually cleaned and disinfected to a certain extent. Next, please. There is a very interesting project that we worked with. This was a Paharpur Business Center in Delhi, in Nehru Place. Nehru Place has actually got one of the most contaminated airs. Sir, actually, I have sent a video. Could you put that video up over here, please? I think I'll let the video do the talking.
Sir, is that a link in the PowerPoint?
Yeah, I've also sent the video along with the presentation. Or I could put it up from here if you want.
Yes, sir. You can share a window and you can open the YouTube. You can use a share a tab feature that will make the sound better.
Can you see it?
Yes, you're able to see your video screen. No, it's not playing any video yet.
Sorry?
It's not playing
Can you
any
see
video.
the video?
No, I can see a black screen.
So could you see the video?
No, sir, we could just see the black screen. The video was not playing. Can you share the video file with me?
I've shared the video file.
Okay, I'll check.
Otherwise, it's okay. We can carry on. I mean, if we are running short of time.
Okay, sir.
If you can just go back to the presentation. Okay. What I'll do is I'll try and make sure that I put up the video at the end of this talk. What Mr. Mittal has done is he actually found that there are 3 species of plants which generate as much oxygen as is required by one person in a day. So one of them is Erica palms. So what he has done is he has put about 4,000 Erica palms on his roof, and he is drawing in outside air from this greenhouse. And you have a lot of fresh oxygen which is being pumped into this building. Now, his building is located in one of the most polluted areas of Delhi, which is your Nehru Place. And when you actually walk into his building, it is almost as if a whiff of fresh air has hit you. You actually can feel the amount of additional oxygen that you have in the air when you walk into his building. So he has done this experiment about 5 to 6 years back. And what we are trying to do in one of our projects is that we actually have terraces on our high-rise building, and we have put up vertical gardens. And in these vertical gardens, we are trying to find species of trees which may not generate as much oxygen as, say, Erica palm, but still will generate sufficient amount of oxygen so that this oxygen can actually be pumped into the building. So you have terraces which actually act like lungs and purify the air, and then that air is pumped into the building. Next. The next component of wellness is thermal comfort. And somebody has very rightly said, the right temperature begets the right temperament. So typically, a building which is thoroughly comfortable, the occupants have efficiency which is much greater. In fact, whenever you have improper cooling, the efficiency decreases by about 6 to 10%. Next. So, for thermal comfort, there are 3 major parameters. One is, thermal comfort control. So, like I said earlier, with an improper ventilation system, what happens is that, you have cold spots and you have hot spots. Also, what happens is that each person has got their own individual temperature that they are comfortable at. There are some people who like to have their room chilled, and there are some people, who are comfortable with warmer temperature. And typically, such 2 people are married to each other. So you have a lot of people with, what I'm trying to say is that, you have people with different thermal requirements. And the idea over here is to make sure that, you have thermal comfort control the way you have on an aircraft, where, each person actually has got a small unit on their desk, which, has airflow. And, person can control how much, is the temperature and what is the airspeed that they feel on their face. The next is relative humidity, and need to have mechanical systems which make sure that RH remains between 30% and 60%. In places like Mumbai, which are very humid, the idea is to actually make sure that you dry the air, and this drying of air may happen by preheating it and then cooling it again. But the challenge is, when you are in places like Delhi, where during winters, your RH can go as low as 15 to 20%. I have lived in Delhi, and I've often had, nosebleeds in winters. It gets dead dry over there. So there, you actually need to add humidity. The third is free seating. This is a new concept where you actually have an office, where you have an open office which is designed in such a way that you have a temperature difference of 3 degrees, up to 3 degrees in different parts of the same office. So you say you have an office which is designed to have one part which is designed to have 21 degrees, then you have another where you probably have 22, and then you have the third one which is at 24 degrees. Okay. And you have free seating. You do not actually assign a seat to a person. You cannot tell a person that you have to sit over here. The person can actually choose where he wants to sit or she wants to sit based on whatever temperature he or she is comfortable at. So you have free seating. So this is another concept which is coming up. Years back, when I talk about years back, I'm talking about probably mid-90s. There was a building which was designed in Bombay called, it was a CMC building. I don't know if you've heard of it. It's in it's in Bandra, where the building has been designed in such a way that you have open offices which are divided across 4 different floors. Okay, so the not 4 floors but 4 different levels, where you actually have a difference of just about 5 to 6 feet between different levels. And each level is cooled differently. And what happens is that the levels are designed in such a way that you always have interaction with each other. You can walk up and down. So it actually promotes movement. It has different offices at different temperatures. And, no person is given a fixed workstation. So when they log in over there, based on their requirements and based on the way the office is, filled up, the person is actually told that you can occupy level 3A or 3C or 4B or 4C or whatever. So you have different temperature which is being controlled, and also all people who are like-minded are put in on one particular floor in one particular open office. I believe this office is still functional, and unfortunately it is not much published. That is irony. Next, please. This is the Singapore Building Construction Authority's office. So if you see this particular office, it has been designed as a sustainable building because they believe that you have to be sustainable first to be able to preach sustainability to the others. And the way this building has been designed is that you have light shelves which prevent glare from coming in. Still, they reflect sufficient daylight deeper into the building. If you see, almost all workstations have task lights, and this little white device that you see right next to the person's screen is actually that thermal control device that I was talking about, where this is like a small fan, and this fan actually pushes in cold air, and it has got its own thermostat, where the user can control at what temperature they want the air coming in, within their own cubicle. And of course, you have flow diffusers. So you have air which is coming up from the below the floor, and it is slowly rising up. And of course, you also have CO2 sensors which control how much fresh air is coming in. So this is one holistically sustainable building that has been designed by the Singapore Authority for themselves. Next, please. Connectivity to nature is very essential, and this forms a very large part of how we work. If you actually give visual access to a person to any space outside, they tend to perform better. I actually have a couple of interns from my office over here, and they can probably tell you that we have designed our own office in such a way that each seated occupant actually has got a certain amount of visual access to something which is, green from the office. Next. Now, when we talk about visual access, you also have biophilia. I'm sure Dheeraj covered this yesterday. Where you are actually bringing landscaping within the building. You have atriums with vertical landscapes. You have atriums filled with indoor plants. But I would just like to share one experience that we had with a project that we did in Mumbai, where we actually had a butterfly garden in the atrium. And because we had the butterfly garden, the species of the plants which are brought in were, specific to what the butterflies would be comfortable with. Now, what used to happen in this particular building was that every day at 9:30 in the morning, when people actually come to, their office, the CO2 sensors would go off. The CO2 sensors would actually sense a very, very high level of CO2. Now, typically what happens in a building is that, throughout the day when people have occupied the building, throughout the day people are breathing out. At the end of the day, at 5 o'clock in the evening or at 6 o'clock in the evening, you actually end up a very high buildup of CO2. Now, instead of this happening later in the day, they started happening earlier in the day. And it took us a week to figure out that the reason why the CO2 concentrations were very high in the morning was because we had chosen certain species of plants which throughout the night were putting so much CO2 into the building that by the morning, the CO2 levels were actually unhealthy for human use. And ultimately, we actually had to go in for a night purge, where throughout the night we were actually bringing in outside air and purging the building. Suraj, unfortunately, has just left the meeting, but he was one of the people whom I worked with on this particular project. Next, please. When we talk about outdoor access, Kenyans building I talked about earlier. But even if you look at the Kanchenjunga designed by Charles Correa, in 70s or 80s, without having any rating system or without having any concept of wellness, this building has been designed by a master architect in such a way that each and every space has got connectivity to the outside. You have sky courts, you have actually courts from where a person can see the sun, they can see the sky, they can see the outside. A beautifully designed building. And if there are any students over here who wish to take up a thesis subject, then one very good subject would be to analyze how green this particular building actually is. Just see if this building were to go in for a LEED rating, would it get a LEED rating? Would it get a IGBC rating or would it get a wellness rating? And I would be very, very, very surprised if, Kanchenjunga does not get, a gold or a platinum rating. So these buildings have been designed with courtyards, have been designed in such a way that, the users in a tall building can come out and feel connected to the nature. One of the complaints against tall buildings has been that people in tall buildings, when they occupy, when you are on the 40th floor or when you are on the 50th floor, what happens is that there's a sense of disconnection with the ground. That, people don't feel as if they're grounded. They feel as if they're uncomfortable. When you are spending 8 to 10 hours a day so high up, people are uncomfortable. But actually, if you were to have such sky terraces or sky courts, then who knows, it might add to a sense of psychological comfort. One would feel grounded in a tall building. Next, please. Next is Community Connect. Next. So here, if the building were designed in such a way that, there is certain amount of glass facade, or there's some art object which is right in front of the building. The top photograph, of course, is a very famous Rockefeller building in New York, where it has got its iconic statue in front. You know what this does is, such plazas, what they tend to do is that they tend to create spaces which are interactive, which promote social interaction with the people. You do not feel as if you are isolated. So you have artwork, you have benches, people sit around there. You have spaces which promote movement. Where you are comfortable moving around. Which is good for one's physical health as well. So you have community spaces where people can actually say you have a flight of stairs. I do not know if you have such spaces in your college, but I'm sure you do. If you have staircases, people tend to sit over there if they're comfortable and wide enough. So any building which has got such spaces, what they're doing is that they are contributing to a certain level of social sustainability, which is what wellness is all about. Next. Also, if buildings are designed where you have certain aesthetics which appeal to the end user, one feels connected with it. One feels, as if they are, there's a sense of belonging that a person feels to a particular space. If they can culturally connect with it. Say if you're working in Japan, or if you have a Japanese working somewhere, and they see the Zen garden over here. There is something which is so Japanese. There is a sort of immediate connect to, for them. There is this Japanese city near Gurgaon, where you have workers from Japan, and you have, all these Japanese companies which are located over there. You have Hitachi, and you have Mitsubishi, and you have all of these companies over there, and you have all of these Japanese engineers who come over there. Now, these people cannot stay over there for a long time because they feel very disconnected. But say if they were in a building, where they could feel culturally comfortable, where they could feel a sense of belonging, that would add to their well-being. They'll probably be more productive. They'll probably be able to stay longer over there. Next. Also, actually, they have just skipped a slide. Can we go to the next slide? Yeah. So similar to what you have for the Japanese. I think we have Anuja over here. Anuja was involved with the design of Mudra, and the way you have this worldly art on the walls. The way you have icons in this particular building are such that your users actually feel connected to it. There's a certain Indianness which is there, to this building. So such icons, make a very, very significant impact on the users. Certainly, aesthetics do. If you see the image on the bottom right, this is the Hubble Cafe at Godrej. Godrej Boys at the factory in Vikhroli, where they have actually created a workspace where everybody can come in. You have a lot of interaction over there. They have a cafe over here, and unfortunately, I could not get a photograph of artwork that they have over here, which has been made from all old Godrej typewriters. Now typewriters are extinct, but they have actually collected all these typewriters and they have actually made a artwork out of it. So the employees of Godrej actually feel a connect to it over there. Next, please. Now the question arises that from where did all of a sudden did this wellness come into the fore? And if you look at some numbers over here, say if you have a building which is typically say 10,000 square feet, and the cost of construction of such a building, assuming 3,000 rupees per square foot, comes to about 3 crores. And you say have 100 people, assuming that you have one person per 100 square feet. So say you have 100 people who are working over here. Say the annual salary of this 100 people is about 10 lakh rupees. See, all of these are very plausible numbers. Huh? These are not numbers which are vague. They're very plausible numbers. So you have an annual salary cost to the company of about 10 crores. Okay. And now just imagine that if you have even a 5% loss of productivity because of poor indoor space quality or indoor air quality, what happens is that the company loses 50 lakh rupees every year. So in just 6 years, they would have lost whatever is the total cost of construction of the building. Okay. So now if you look at the economics, this is where wellness is. This is why wellness is all of a sudden come to the forefront. People have started realizing that the most important commodity on earth is not your petrol or your diesel. It is the people who is the most precious commodity that you have. And that is why now with buildings, they have come to the forefront. Next. So sustainability is no longer just about energy efficiency, it's also about well-being, it's also about people, and that is the way it should be. Thank you.
Thank you so much, sir. It was a wonderful presentation. You started it with a very interesting statement that tall buildings and sustainability put together seems like an oxymoron, but I think through your presentation, you proved quite the opposite. I think it's a common perception that tall buildings are not sustainable, but as we know at the urban level, a high-rise, high-density model has been found to be more sustainable compared to a more dispersed kind of development. And through your presentation, you've touched upon all aspects of sustainability at the building level and highlighted that energy efficiency, water efficiency, creating healthy and livable spaces are all possible at the building level too. And it is possible to achieve the triple bottom line of people, planet, and profit. So thank you so much for this presentation. I would request Professor Shrutika, who's the moderator of the session, to proceed with the question answers.
Hello, sir. So we have one question on the chat box. Professor Mandar Duri has posted this question. Sir, would you like to address that?
Sure.
Professor Mandar Duri.
I think Shrutika, you can go ahead, no issues.
Okay, fine, sir. What kind of integration is possible of form, structure with sustainability aspects if one wishes to learn from the contextual natural aspects?
That is, a very, very tough question, but yeah, it's a very appropriate one as well. So I understand what you're asking is basically how to blend form and structure and also nature. So yes, if you see some of the buildings that I showed earlier, say Kenyang's buildings, the way they actually seem to be spiraling up, the way you have your landscape also rising up, the structure also is designed in a similar fashion, in such a way that your form, structure, and nature is integrated as one. So you have a building where you have the landscape curling up. You also have certain buildings which are designed in such a way and they have to be because tall buildings, wind pressure is a very big issue, and you have to design the structure in such a way that it sort of offsets the wind breaks in a way where you do not add any more wind load or wind sway to the buildings. I do not know if this is the answer that you are looking for, sir.
For example, what I was looking for is how do I harness maybe sun energy? We all know because we say that let's use the panels and optimizing that. We also have glass which can have the solar component. So those things are there. You have a glass directly used with a film which will give you the solar energy. Then because solar is prominent, so I'll probably just skip a little bit. But if I look at it reverse way, if I say that I want to bring in shade, largely we look at things in which we say let's have shading elements. It's a very passive approach. But if we just put in some iota of kinetic aspect to it, I think the previous speaker also had brought this point that Gautam in fact was saying that kinetic may not be a good approach, but I'm trying to look at it from this point of view. If I understand that, let's say for example, my building is in the desert, like what we have as the Burj Khalifa in the desert, and we have a hot dry climate, and I'm learning from nature, trying to learn from nature. I'm looking at maybe the most prominent plant situation that happens in that kind of climate because it survives. So maybe those mechanisms, maybe those kind of systems, processes which occur within that kind of a plant, if those are studied would it be able to give me some kind of an idea of how the form can be created of the building? How can the openings of the building be created so that they can respond to this idea, learning from there, so that I get a start point for imagining the duties of the form themselves from a sustainable point of view, so that I don't have to fitting some what do you call most of the times students design buildings and then later on they start making it efficient or functional. But in the first place, if the tall building itself takes this into account at the outset itself to be sustainable, this could be an approach where you start looking at mechanisms around you, which are already there. Nature probably is the most smartest that we can see. It is by far the smartest mechanism that I understand. So I'm saying if these ideas, can they generate a good form? Can they give a different system, which can probably lead to a better solution eventually? That was the question.
Okay, sir. It's a multi-part answer that I have for this. One is, you're talking about, not just the students, and what you said is very true. Even architects, we tend to design the building first, and then we try to see how we can go about making it sustainable, which is actually not the correct approach. What would be the correct approach is that we, actually see where you are designing the building, what is the scope of the building you have. We actually figure out what is the most optimum form that you can go in for. For example, when we were doing IGBC's own building, Indian Green Building Council's building in Hyderabad, one of the first things that we did as a part of our analysis was we told them that if you go in for a circular form, you have minimum surface area for the amount of space that you have inside. So your wall area is minimum for a maximum carpet area. And it was feasible for them to do it. So that is why, we actually, if you see that building is designed in a circular form. Similarly, we actually do studies to see what is the most appropriate form that you can have. For example, if you go in for a square form is one of the most inefficient forms, okay? Because you end up having a very large power area which you either need to heat or cool down. So say, you have a periphery that you are cooling down, then you have a center that you are heating up. Or if you have a periphery that you are heating up, then you need to cool down the core. It always works, opposite to each other. So square form is inefficient. So the same way, you actually work out what is an efficient form, number one. Then the other thing is that you actually need to work out what is first we're talking about the passive side of things. To work out what is your, window to wall ratio, how much fenestration should you have, where should you have it. Okay, that is how one would go, there is a process that one needs to follow. That is part one. The second is, you're talking about generating energy when you're talking about solar-powered windows, where you're actually talking about what is called building integrated photovoltaics. Yes, the tall buildings have a very, very large vertical surface, but typically, whenever you have solar photovoltaics on any vertical surface, they are highly inefficient and very expensive. So you need to work out a balance between capital cost and the amount of energy that it will generate. In fact, there is a building that we are working on, which was a tall building in Mumbai again, where we initially thought of putting up a windmill on the roof, okay, to generate, because you have high wind speeds, your coastal area, to generate a significant amount of energy. But then if you see the cost of putting up a rotating blade structure on top of a 100-meter tall building, and if you see the structural load that would come in, and if you see the cost of structure versus the amount of energy which is being generated, the amount of resources that are being poured into the building in terms of additional steel and concrete, then is it worth it or not? So you actually need to do cost benefit analysis for any one of these sustainable strategies. There was this Indira Paryavaran Bhavan in Delhi, where they decided to go in for bore wells, where they were actually using the earth to cool the water, and then they were passing that cool water through their buildings. Now they have close to 60 bores, which are about 200 to 300 feet deep, just to have 60 tons of air conditioning done naturally. So you need to figure out whether it is worth it or not. So these are two things. And then, of course, you are right. Nature does give a lot of clues on what is appropriate in a particular place. And more than nature, what I have found is that if you look at the vernacular architecture of any place, it gives you a very good clue on how to go about designing in that particular place. If you are designing in Jaipur, you need to have thick walls, you need to have a small courtyard. If you are designing in Mumbai, then you need to have a building and you need to have a corridor all along its side in large windows. Okay, I mean, even if you look at the vernacular forms, it will tell you the same. So this is how one would take clues, if not from nature, at least from vernacular architecture.
Thank you, sir. Thank you.
We have one more question by we have a question by a student, Dream Mehta. So she's asking if you could give any other alternatives to the construction material like RCC for RCC. So as a student, she's finding timber as the most viable material, but it is looking at the other side of it, the top side of it, it is very expensive and plus it's combustible. So she's asking if you could address on some alternative materials in the construction for the tall buildings.
See, for alternative materials for low-rise buildings, bamboo has been considered. Steel reinforced bamboo is used. You have glass reinforced concrete, which is becoming very popular now. But when you want to go in for a tall building, when you want to go in for a building which is more than 70 meters, then you need to go in only for structural steel. There is no other material which has got that level of workability, cost, weight, and strength. So, when you go in for tall buildings, you have restrictions on what materials that you can use. But yes, for low buildings, you can actually go in for bamboo. You can use. There's a lot of scope of using recycled materials for your low-rise buildings.
Okay,
I have something to say here. I mean, in continuation with what Mandar also asked. Mandar, there is one more thing which I think Ankur forgot to mention, that first of all, you can run when you are planning, you can run energy simulation software. Now that helps you in a big way architecturally to analyze that how the plan should be done. And typically when we approach for green building, that time we do the energy simulation. But the best way is when you start moving your pencil to run this energy simulation, to simulate your building and see that which is the way you can mold your form, mold your design. And that will help you in a big way to work on the daylight. There is a daylight simulation also. So these software can help you at the initial level to analyze your design and come to the practical in-between approach, because that is also very important when you are designing for the developers. So it could be a bridging gap between what you want to achieve. So these softwares will help you to finally coming to your score chart, as well as to work on your efficiencies, and as well as define your materials. Like whether you want to go for a solid panels or whether you want to go for a glass, where you want to restrict your glass, where you want to go in, where you want to come out, where you want to use your maximum energy of kinetic facade, or you can have all that sort of a combination. And answer to the girl who has asked that question, yes, but there are concrete also started giving an option with the fly ash content, where you can work around with your emitted energy. And second material is a steel, which has large amount of recycling content. So you can look at these material, but as pointed out by Ankur, for the high rises, for the fast execution, for modularity, which was the point yesterday raised by even Yogesh. He talked about the modular kind of a system of construction, where there's a cost, time, recycling materials, making them easily available. So it's not only material which is executed on the site, but the amount of energy which has been utilized while making those materials can also be controlled. So this is what the holistic picture of the green building, and it's not in isolation with your own building. So when we are choosing, you are choosing for the planet Earth and not for your own project. So that's how the green building concept is looked upon. So single high rises is impacting your entire neighborhood, and that is something which needs to be looked upon. So I think that's what the green building is, isn't it, Ankur?
Absolutely. I mean, you hit the nail on the head.
So the next question is by Professor Ajit Nirmal.
Yes.
He's asking if you could suggest some case studies for the students with respect to the green certified buildings in India or abroad?
Sure. There are a lot of case studies that you can take up. There are a lot of buildings in Mumbai itself. So I'll be happy, depending on what sort of a thing that they're looking at, I would be happy to suggest a case study for them.
Sorry, my question
There are a lot of buildings
included. Sorry, my question included tallest buildings. Any taller green certified buildings?
See, among the tall green certified buildings in Mumbai, you have the Kohinoor Square Tower, which is going to be hopefully a gold certified building. For residential buildings, we have recently completed two 60-story buildings for Bombay, which is the Island City Center (ICC) buildings, which incidentally Anuja's office has designed. These are residential buildings. These are LEED gold certified buildings. So yes, they have a lot of glass to them, but they also have been designed in such a way that they consume at least 20% less energy than a conventional building. So you can take up these case studies. And of course, when you talk about tall buildings, there's also the Kanchenjunga, which I think is a beautiful building, which, if somebody actually tries to see whether it can get a rating, it would definitely get a gold or a platinum rating. So besides this, also you have the Palais Royal. You have a lot of buildings in Mumbai, which would be ideal case studies. So depending on what factor you are looking at, I would be happy to recommend them.
Okay, sir.
I think if situation permits and if we get permission and students are agreeable from all fronts, if we can arrange for a meeting, site visit to a few of the tall buildings, if the management of the tall building also allows.
Sure.
We will work that out and we can, I think students also would learn through that site visit would be more important. But only thing, there are multiple fronts we'll have to take many permissions and others. So let's see if that is doable in Mumbai right now.
Anand sir, what I can do is, in fact, since Anuja is here and she is working on a lot of sustainable tall buildings as well, she can also be of help. And there's like I said, different elements. What is it that you are looking for? We have done a ventilated cavity building in BKC. This is a JSW building. If you want to look at a ventilated cavity, we can go over there. If you want to look at IBMS, we can go somewhere else. So depending on what is it that you are specifically focused on, we can.
The target could be not just a tall building or some. It could be specific to probably certain aspects of the building and around. Yeah.
Yes.
We'll work it out. If students agree, we will work that out. No problem.
Okay, sir. I think we should give some time for the students. They will definitely come back with some more questions after the break.
I think there is some question.
Over to Shruti.
Shruti, there are some few things, I think.
Yeah, there's
Okay,
a
okay.
question
Yes,
in the chat box. Jay Keskar, if he can unmute himself.
Jay
and ask.
Keskar, yeah. Okay, so what are the incentive for the developer to go for the green building with the higher capital cost?
There are, depending on which part of the country you're talking about, there are quite a few incentives. Pune, for example, gives you almost 10% extra FAR for a platinum certified building. It gives you 7.5% for a gold certified building. If you come to Gujarat actually gives you a 5% discount on the premium FSI. Noida gives a flat 5% additional FAR for going in for a green building. So basically, you have two types of incentives. One is additional FAR, the other is reduction in premium that you pay for approval. So these are two forms as of now. And a couple of years back, the SBI actually used to give 1%, interest, which was reduced by 1% for a green building or residential home loans. So these are the three different types of incentives that you have.
Okay, sir. So we have one more question. This was in fact asked by our Professor Aparna Rao yesterday. So if you could also answer this question, sir. What are the typical structural or service factors to be considered while proposing the private terrace gardens or green balconies at the higher floors while designing the high rises?
Could you just repeat that? I didn't understand what was the relation
Yes.
to structure.
What are the structural systems or the service factors that one should consider while proposing the terrace gardens or the terrace balconies at the higher floors while designing the high rises?
See, in a high rise, whenever you have a terrace, the most important factor, of course, is your wind load. What happens is that when you go above a certain height, say when you go above a height of 50 meters, even operable windows are a challenge. So if you have a sky deck over here, the deck has to be properly located in such a way that it isn't a wind break. It should not be in the wind zone. So that plays a very significant. That plays, in fact, plays the most significant role. The rest, of course, is structural, and probably Yogesh would have been a better person to take it up, or Anil Hira would have been a better person to take it up.
Okay, sir. I think most of the questions have been answered. So, yeah, over to Shruti.
Yeah, thank you, Shrutika. Thank you so much, sir, for taking out so much time for our students. This interaction means a lot, and I'm sure it's going to help them when they are going to be in their working for their design project. So thank you so much. On behalf of VESCO, we would like to present you with a token of appreciation, a small memento from our side.
Thank you.
Thank you so much.
Thank you, sir. Thank you for taking out your time.
Thank you.
Thank you, sir.
We will now take a break. Our next presentation is going to start at 1:50. So I request the audience to join back at 1:50. So we are breaking for almost 1 hour right now, and we'll be back. We'll start with the next section at 1:50. So please do not be late. We have the last presentation on architectural design.
Yeah, so it's all the students should understand now. We didn't keep intentionally the design part ahead. We kept it at the end, and all the technical subjects and the ancillary additional subjects were taken up first. So you have the background of each one, right, from MEP, facade, structural, landscape, sustainability. Now, how does that all get connected to the design part of it? So it would be very important point that you need to be present and more attentive. And with all these, how do you integrate back onto the design? What are the issues which come? So please come on time. 1:50, 1:15 should be. 1:50 all should be there. Thank you. Thank you all.
Thank you. Welcome back, everyone. We have the final presentation of the session, and it is by architect Pranav Desai from IIG Consultants. He will be presenting on the topic architectural design of tall buildings. Architect Pranav Desai is the principal architect of the award-winning architectural firms IIG Consultants and Atul Desai Consultants. For over 25 years, he has contributed to the design and real estate communities in a variety of contexts. His background encompasses master planning, large-scale residential development, workplace design, and institutional buildings. He has a bachelor's degree in architecture from Sir J.J. College of Architecture, and he has worked with Skidmore, Owings, and Merrills at San Francisco office on varied projects from housing to airports. We welcome you, sir. Over to you.
Thank you. Thank you very much. Can I start? Am I audible?
Yes, sir, we can start.
Yes.
You can share your screen.
Thank you.
Yes, sir, we are able to see your screen now.
I think you can't see it now.
Right now, I can see the Google Meet window.
I think we are facing some technical issues at his end. Let's just wait for the speaker to come back. While the speaker joins in, I just wanted to remind the students that if you have any questions, please type them in the chat box during the lecture. Do not wait for the question answer session to start because many times there isn't enough time left for your questions. So please, as and when these thoughts come in your mind, please type them in the chat box and you can ask these questions to them during the question answer round.
You're on mute, Pranav.
You can see the screen?
Yes, sir, we can see your Google Meet window right now. Yeah, the PowerPoint full screen is now visible.
Okay. So basically what I'll do is that, first I'll just run through a few of our projects and, explain like how we have achieved, certain, parameters of the design, the efficiency of the core, what was the basis of the planning, a little bit about the DC rules, etc. a little bit about the sustainability of high-rise buildings, and basically the methodology of construction, etc. And also what was the basic parameters and what was the thought process of designing the projects the way it is. So I'll basically share 5 projects. 3 are already built, 2 are on the design stage. So as the time permits, if we can just go through it like quickly, and if you have any question answers, just butt in, because I don't think there'll be time to go back to that project again. So everybody must have given you a brief about tall buildings. So what exactly are tall buildings? So there are various definitions of tall buildings. A building which is higher than 50 meters in height is called a tall building. More than 100 is termed as a skyscraper. More than 300 is termed as a super tall building. And above 600 is a mega tall structure. We don't have any structure which is more than 600 in India, but there are projects which are built up to 300, and there are many which are getting built between 100 to 300 meters. But we don't have much happening 300 plus. And as far as the current DCR is concerned, anything which is above 70 meters is termed as a high-rise building. So why do we go tall? The basic parameters are scarcity of land, increase in demand for residential or office spaces. The plot sizes are smaller, and we need to build more in terms of densities, economic growth, technological advancements. Human aspirations to build higher means there is always a kind of a need to go higher, because there is going higher means that it is like it is termed as if you are like there is some kind of an economic development, and there is a race to compete for the title the tallest building. Like Malaysia did it, now Dubai is doing that. So it's just the reason for being going tall is just that the city comes onto the global map. So there are certain countries which just want to build tall just because of trying to compete with the race of being tall. Now, what influences design of tall buildings? The basic the parameters are development control rules, structural design, form and function, climate, and sustainable parameters. But the most important 3 are market forces, end user requirement, and construction technology and methodology. So actually, the first 3 really determines the design of tall buildings. Market forces, in the sense, is that whether going tall will the end user prefers to go tall. So that's one of the reasons why developers are going tall. End user requirements is like, because of proper ventilation, or in terms of, views, you get taller buildings which are more premium. And construction technology and methodologies, because, technology and in construction is improving day by day. And that's one of the reasons why you can basically, go taller and explore, various forms of construction, like steel construction, prefab construction, slip form construction. So there are various methods in which these technological advancements are, possible. So there are few projects which I will just run you through, and basically it will talk about all these parameters, but the most important 3 are the first 3, the market forces, end user requirement, and construction technology and methodology. After So once these three parameters are fit in, then comes the DCR, development control rules, structural design, MVP design, form, climate, sustainable parameters, etc. These are the typical, typical floor plans of the tall buildings which in and around Bombay. Like, this is the 1973, which has got a central core with flats on the sides. So the core is basically all shear walls, and then you have these bulk columns on the perimeters. So this is one type of configuration which is there. This is a squarish configuration where the core is off-centric, and the flats are placed in a U-shaped form. And there are 4 flats on a floor. This is the Loda Altamount road, which is just one flat on a floor with a core which is like half in and half out. And this is the park. This is Ahuja at Worli. And so basically, if you see like a common denominator of all, you can't see the screen.
Right now we can see your Google Meet window.
So the basic parameters is that the center core is a kind of a strong feature of the building, and the units are all like encompassing the core. Conceptually, that's what tall buildings are all about. Now, if you see a T-shaped building, again you have a central core. If you have a wing-shaped building, again the core is more central, and the structure is basically symmetrical to that core. Now, in terms of this plans, this is one of the most efficient, number one, because the core is in the center. The entire thing is wrapped around. If you have like a wing-shaped building, linear, or if it's a T-shaped building, it's not very efficient in terms of structural design. But there are many other parameters which are required, in terms like a T-shaped building may be better in terms of exploiting the views, or a T-shaped building will be better in terms of giving ventilation to the units. So every building has a different set of parameters and how it fits onto the plot. So these are the 4-5 projects which I'll be running through. This is the Amantra Towers at Kalyan, Excalibur Towers, which is at Mahalakshmi, Vivaria Towers. These 3 are completed. And if we have time, we can just run through the 4 and 5, which is more on the design stage. So this is a very affordable housing project. It's almost in a site of around 15 acres, and basically it has a construction area of around 50 lakh square feet. Now, one of the parameters, the basic parameter of this layout, before we worked on the layout, we came out with many options, and then suddenly there was the client, after like maybe 6 months down the line, they said, okay, we don't want to construct this project in phases. We want to construct all 50 lakh square feet in one go. So the methodology or the thought process of the design had to totally change. It had to be more construction friendly. It had to be more modular in nature. So it had to be more flexible in terms of planning. You couldn't do like multiple options in terms of the core design. You couldn't do multiple options in terms of the tower design. Like there had to be certain element of repetition when it came to building faster and building more efficiently. So what we did is that we basically oriented, the towers angular, and because of the wind direction. And the primary reason of placing these longer towers and a shorter tower in between was basically the red circle is the diameter of the crane. So the entire concept was derived along a construction technology, or in terms of a construction, the way you can build faster. So the typical floor plan was in a Maiwan construction. Maiwan is like an all concrete formwork system, and in order to lift the formwork from one tower to the other, there was a central, a crane which was placed in the center, and that basically took care of two towers. So if you do an overlap of that, is so basically what happens is that these linear towers are the taller ones, and the shorter ones are the ones which were done later on. So these are the 30-story towers, and the bridge connections are the shorter 12-story towers. So this is the view how the project was. So what you see is that the taller buildings, 1, 2, 3, 8 to 9 tall buildings are there, which are around 35 stories, and the smaller ones are where the crane was installed. So once you reached the top of the shell, then the crane was dismantled, and the shorter buildings were erected. And this entire project of 50 lakh square feet was constructed in a matter of like 3.5 years, the shell, and another 6 months for the basic finishing. This is the basic configuration of the units. Now, this is the typical floor plan. Now here also, if you see, this is one tower, like one tower, and the second one is the identical tower, but it's like mirrored. So this is your line of your. So this is the same tower, but it is like flipped and mirrored, and it is connected between each other. And again, you have the concept of having the central core and 4 flats on a floor, 3 lifts. So the core is actually the strength of the entire tower. And again, when you're designing residential towers, you need to keep this perimeter in one line. As many offsets you can reduce, it's more efficient. Structural consultants, MEP consultants, contractors are all happy if you keep this in one line. Again, somewhere, these kind of grids also you need to keep in line. But sometimes, when you're planning the units, you don't get to have that kind of a benefit. But so conceptually, you have this as the core, and the flats are 4 flats on a floor. Now, 4 flats on a floor it's like it's not a very efficient plan as far as the ratio between construction to the carpet area is concerned. You need to at least pack around 5 to 6 flats on a floor if you are going more than 35 stories. So again, you have this combination of a low rise and a high rise building where this is around 35 floors and this is 12 floors. So this is where the crane was installed for 2 towers. So where I'm coming from is that when this design was envisaged, the basic parameter of design was not sustainability, it was not orientation, it was not even to some extent exploiting the views. It was more on the way you can build faster in terms of use of construction technology and methodology. And another thing what we have done is that, we have bridged the, this is the tower, and we have not kept a core in the smaller tower. This is a 12-story building, but there's a kind of a connecting bridge which connects the 12-story building. So we have not repeated a core in these smaller buildings because of efficiency. So now there are 6 flats on a floor till 12 floors, till the 12th floor, and above that it becomes 4 flats on a floor. So you have this combination of these high-rise buildings, 1, 2, and then connected by low-rise buildings of 12 floors. You can see these are all tall buildings, and the lower ones are all shorter buildings. These are the shorter buildings, and the entire build the site is covered by a 2-level car park and 1 basement car park. So there are almost close to 2,500 cars. This is the sale tower. This is the project we are talking about. This project is under the rental housing scheme of the government of Maharashtra. So we have to build a rehab component also, which is this, and this is the sale component. The sale component is around 50 lakh square feet, and the rehab component is around 20 lakh square feet. And this entire project was built in 4 years because of the construction technology. So here the primary design criteria was the use of construction technology. It was not sustainability, it was not views, it was not anything other than that. This is the combination of low and high rise buildings. This is the view of the completed project. This is another building which we have done at Mahalakshmi, which is again totally a different project, where that was basically 15 acres. This site is only around 1.5 acres. So this is the race course, and the site is basically very close to this is the view from the site. This is the site, like where basically the site is broken into 2 parts. You have this one chunk, and this is another chunk, and there's a road which divides the. This is a kind of a road, and there are 2 portions to the site. So again, this is under the 33/7 redevelopment project, where there are tenants which are there on the existing site, and you need to rehouse them in a building, and the balance area is for sale. So you have the site which is basically divided by the road. This is 1, 2, and this is the road which cuts the site. And this is Jacob Circle. So you basically go around the Jacob Circle, come to the sale building. And these are the 2 rehab buildings. Rehab buildings are only 70 meters, and the sale is going higher. So this is the, I just wanted to come, basically to explain you the typical layout, and then come back to the parking grid. So in this project, what we have is that we have 2 flats on a floor. And what we have done is that we have, kept the core at one end of the building. It's not, coming in the center like the other plans which I showed. It's basically at at the corner. The reason being that this is all parking. So you have a driveway below, and then this is the park. So now another very important thing you need to know is that when you're doing high-rise buildings, you cannot float. The minimum floating of columns is 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 a happy situation, and this core has to go from all the way from the ground till the top. So the location in which you put the core is also somewhere related to the parking which is coming below the tower. In this case, because it's a smaller site, the parking is exactly under the tower. There is no place to park, like around the building. There is no podiums. This is basically the parking. The tower, below the tower, there's a 4 level of car parking with the car lift. So if I were to put the core in the center, then it would obstruct the parking which is happening the driveway, and I have to float columns. So the way you plan your tower is basically the structural grids needs to be aligned with the parking grid to avoid minimum floating columns. You can float some 1 or 2 columns, but like you cannot float. So this is the concept. Like you have the driveway. This is the typical floor plan. You have the driveway, and you have the car lift. So the driveway is absolutely clean of all columns. This grid is totally free. And this core is the structure. Structurally, this core gives rigidity to the building. So no structural engineer will allow you to float anything in this area. You can float like few columns in this area, but if you avoid floating, that's like it's the way you need to design buildings. So this grid basically is totally column free. You have columns, driveway and parking on both sides. So where I'm coming from is that you need to plan your typical floor and your parking more or less in sync. It cannot be you plan your parking and a typical floor and then you fit in the parking. It has to be like kind of a one exercise, because even this distance between this to the end is governed by your 6-meter driveway and 4.5 meters parking way. So these are the projects which you will be working on when you actually come out. So this is how your typical floor plan sits, and what has to be in terms of planning. What we have done is that all these rooms, which are the primary rooms, the bedrooms and the living room, are all getting either the racecourse view or the sea view, and the core, which is like placed at an inferior location, which is like basically a no view zone. So all this is view. All this is view side. So all the living room, bedrooms are faced towards the sea, and normally there is like in terms of the design of your apartment, you need to give flexibility in terms of changing the internal the spaces by either if somebody wants to take 2 flats, then they basically remove this wall, or if they want to join these 2 bedrooms and make it one, then they have a option of removing this wall or making this wall here and putting a cabinet. There has to be a certain element of flexibility built into the space. Now, because it's a high-rise building, you require 2 staircases of 2 meters. Anything which is above 70 meters in height, code says that you need 2 staircases of 2 meters. Fire chute was as per the old DCR, but now this has changed to to a fireman's lift. So you have to provide a lift over here, which the firemen can use in terms of when there is evacuation or in case of fire. And then you need to give, basically it depends on the sizing of the, if there are 2 flats or 4 flats, accordingly you can size the elevators or the number of elevators. Always there's a freight elevator given in high-rise buildings, because taking material up and down is something which cannot be done through staircases. So very large freight elevators are given in high-rise buildings. So the terrace, always in Bombay, the terrace is like one of the prime amenities, because there is absolutely no space on the ground, because it's a 33/7 project. It's very like highly dense. So the terrace acts as like a recreational or a spill out space. So this is the configuration of the tower, where you have basically a basement for services. Then you have like around 5 levels of parking, which is with car lift. And this is around 30 floors, totally around 130 meters. And the parking floor is basically covered by a GRC jali, because it's one of the reason is you need to perforate you cannot have a dead wall for a parking structure. So the reason for, you have to basically perforate it. And the Excalibur was like a theme. Excalibur is like the name of the sword, King Arthur's sword. So that's how the project had been branded. So what we did is that we basically cut the motives from the sword. We derived a kind of a pattern for the jali, and then that entire screen was put onto the parking structure. This is the jali which was designed on the theme of Excalibur. So now you see the 2 rehab buildings, and this is the sail tower. This is the entrance jali, the entrance hall. This is how it fits into the skyline. This is the sail tower, 2 rehab buildings. Okay, this is another project in Mahalakshmi, where basically it's like it's a 17-acre site and divided into 2 phases, phase 1 and phase 2. So basically it's like a typical in terms of tower design, but I will just like run through project very quickly, because I think we are running out of time. Again, this is a similar view. The Excalibur is exactly in front of this project. So this is like one of the views which more than 50 buildings in Bombay are going to exploit. So there are almost 50 high-rise buildings coming in and around the Mahalakshmi racecourse. So this project was like an old cotton textile mill. And what we have done is basically there are this is like the shape of the project, where we have 4 towers, which are 3 towers which are identical. 4th is a standalone tower, and then the fifth tower is behind with like a public car park structure behind. So the conceptually, when you design, a project like this, again, it's not about the sustainability, structural design. Those kind of parameters come in later on. It's the primary parameter is how the market forces govern your design. It's like what is the end user looking at? What is the size of the apartments which will sell? Uh, if you are building in this kind of thing, if you are having sea view, then how are you exploiting the sea view? Whether your orientation of the building or the design of the building is such that all the flats get sea view, or if one of the tower, one of the flats is going behind. So those parameters come in first, then comes in structural design, then comes in MEP design, and then the other parameters like sustainability and things like that can actually be blended in terms of. But the primary thing is your orientations in terms of what actually the end user is looking at. So here what we have done is, we have taken basically a wing-shaped building. It's like a Y. So every apartment, like 1, 2, 3, 4 apartments get view of the racecourse and the sea. So that's one of the reason to take this kind of a Y-shaped concept. So this is the sea view. So this is all view. Now this, in terms of the efficiency, in terms of the structural design or structural consultant will say that this is not a very efficient design because it's like a wing shaped design. So it's like not like a square. It's not like a core with a square. This is the core, and it's not this. Nor is it like a U shaped. This is the core. The moment you basically put wings to your building, it becomes structurally not the ideal solution, but structural consultants work around it, because the primary thing in terms of design is that every unit needs to get views. So the architecture has to be built in a way that it basically does not go against the market forces, and it basically complements what the end user wants. So if you do a design like this, a Y shape, and each and every room or each flat gets view of the sea. If I had to do like say 4 flats on a floor, then this flat does not get any sea view. Or if I'm doing 6 flats on a floor, then the 2 flats behind don't get the views of the sea. So those suddenly become non-sellable. Those become those become inferior flats. So they have to be sold at lower prices. So they don't mind spending a little more in terms of the structure, but the primary goal is to exploit the views. This is how the site. Basically, this was a cotton mill, and then it was like broken down. And we have these 3 towers with a large landscape garden behind. So basically, we have now totally it's basically 8 acres, and you need to leave a 6 meter setback for the fire tender because it's a podium, and around 12 meters for the tower. 25% mandatory open space is required to be left as greens. And so with this, planning, what we did is, because we were going high rise, only 10% of the plot is actually built up. You have 3 towers and a clubhouse behind. The rest is all green open space. And the reason for putting the towers onto the edge, like on the roadside, this is the roadside. So this open space requirement is only 4.5 meters. So all this portion behind is all garden, which is almost in the tunes of 5 acres. This whole garden is around 5 acres. And every tower you need to leave 6-meter fire tender movement all around. This has to be hard built. You cannot put lawns and things like that. So one of the reasons of keeping it at the edge was to take views, and secondly to keep maximum as green open space in one chunk instead of fragmenting it into many smaller pieces. So what we have done is that because of this kind of a design, we were able to give additional 20% more open space. So that has become a USP of this project, because it's basically very it's all green. It's like there are 3 towers sitting onto this, and the entire thing behind is green. Clubhouse, swimming pool, lot of landscaping. So this is your fire engine track. This entire thing is fire engine. This is full garden. This is the clubhouse with a heated swimming pool. And another thing, this entire thing is, there's 2 levels of car parking which is happening below. So what happens is that you come in on the ground. You come in on the ground. So this is what I was explaining you, that the primary reason of making this Y-shaped design is that every flat gets view of the race course and the Arabian Sea. Each and every flat, and not only each flat, every room of each flat is getting view of the sea. So that's basically the primary reason of this Y. Now here, what we have done is that this portion is the core, which is taken behind. And there are 3 flats. Originally, it was planned as 4 flats. These were 2 BHK flats, but because of the demand, this was basically amalgamated into one large 4 BHK. And what we have is, this is the reason. This is a 3 BHK. Again, another USP of this is that it has 3 sides open. So all these bedrooms get view of the sea. Enter from here, you have your living, your utilities, kitchen, master guest bedroom. Living dining is through and through, so this is fully ventilated. Master bedroom, the kitchen, the servant, the children's bedroom is basically pushed out a little, so that you get view from this side also and this side also. And this side, so it's basically got a corner window. So every room of each unit has got view of the sea. Now another another important feature of this is that, in terms of the structural design, is that because there are large flats, there are going to be these high net worth individuals who will be buying, and their interior designers would like to have flexibility in terms of the planning. So what we have done is that this core is like a rigid core, like it's got like all the shear walls, but the column structure is all bulk columns, large columns which are basically more on the perimeter. And the inside of the building is all block work. So these walls can be all removed, or they can be realigned to make larger living rooms or larger bedrooms, or even some of the walls can be aligned to make larger toilets also. So there is a lot of flexibility which is built in. These are the units. This is the internal apartment. Now, when you again, in terms of the facade design, what happens is that when you're doing like high-rise buildings, you normally make this portion of the tower constant normally because of the formwork system it uses. So only the lower portion is like some kind of a cladding, and the top portion is like a crown which is done in cast in situ. But the entire from the first to the top level of the tower needs to go in one line or it has to go typically because you're using a kind of a aluminum shuttering system. So you cannot change. You can change, but it's not a very efficient way of doing things. You cannot go on changing plans because then your repetition in terms of changes in terms of formwork requirements goes on changing. This normally they keep same, and they do something on the crown and on the lower portion. So only the crown and the lower portion is changed. The rest is all typical. So these are the 3 towers. This is now the 4th one, which is now completed. There's another 5th one which is already under construction behind. So I won't talk about that just now. So that's almost a 65-story building. These 3 are typical. This is a little modified version of the because this is under the older DC rule where the fungible was not there, and this is with these 2 towers are with fungible. So earlier these large decks which you see were free of FSI. Suddenly after after 3 towers, it came into fungible area. So these decks have only reduced to the living room area. They are not going all the way through because then that is under FSI. So these 2 towers are under FSI. So this is how the parking sits. You enter into your come in from here, come into the lift, your lobbies, and then you get into the parking. This is the 2nd level parking, and this entire thing on the top is all no car zone. So it's all pedestrian, landscaping, water bodies. All the parking is happening only on the lower level. So the top is only for recreation. This is how these are the under construction projects. So again, when you're doing the Maiwan construction, you need to see that it's like it's an all concrete building. So there is no brickwork plaster happening on the external face of the building. So entire from this level till the terrace is all concrete. It's all concrete. So even when you're doing the design in terms of GFC drawings, everything has to be thought of, including your switch locations, your grooves, your chhajjas. You cannot change anything because once you get this formwork finished, that means you can't change a single thing into your. So everything has to be pre-planned. You cannot afford any changes once you come up to the first typical residential floor. So first till the 40th is one typical formwork. Internally you can make changes, but externally everything goes in one line. This is the clubhouse. This is a cast in situ. Period shots. This is the facade. Again, it's basically simple. Even these grooves are done in concrete in formwork. All this, there is absolutely no plastering done. and we have these glass railings on the balconies, so that you get the views are not obstructed by like a wall. Relatively, it's a basic clean line structure. This is the back portion. This is the garden, landscape garden, with a clubhouse, heated swimming pool, double height stills. So the lower portion is treated, and the crown is treated, and all this is all in one kind of elevation facade, just like little bit of banding and things like that. This is the ramp which comes up for fire engine. The fire engine tender needs to come up at this level because of the core. But what we have done is that we have made this in a way that the fire engine can go onto the lawn, but there are some grating systems under the lawn, so the fire engine can actually go over the lawn around the building. This is the clubhouse. Again, when you're doing high-rise buildings, this window systems which is used is very, very high-end and upmarket. So lot of time and energy is put into the installing this kind of a window system. Like, so many have got curtain walling also on the facade. But there is like a trend that now, even with COVID, there is a trend that people want the cross ventilation in apartments. They want a little bit of balconies where they can sit out. They want fresh air come in. So the window system is one of the second most important things for a high-rise project. This is a GRC paneling which is done on the lower portion of the building. This is the entrance lobbies, the entrance driveway. So the facade of the lower level podiums where you have the car parking tower. This is all car parking. It needs to be perforated and ventilated. So you can't really have you need to have a perforated facade onto the car parking, because BMC doesn't allow like a fixed facade. Like you can't put glass or you can't put dead walls into a parking structure. This is the view from the night in the night. So what we have done is that every tower, we have basically painted the inside of the staircase in different bright colors. One is green, one is blue, one is red. So when the night, when it is lit, it gives these vibrant colors into the tower, and you can differentiate each tower. Like, so now this photograph has got 3 towers, but currently if you see on the side there are 5 towers. 4 are already built, 5th one is under construction. This is the pool. This is how it fits into the. This is the 5th tower which is coming up. 4th tower. 5th one is behind somewhere. And this is that Excalibur project which I showed earlier. That is somewhere here. Do we have time?
Running short of time, but you can take another 5 minutes.
Okay. So I thought, because this is actually the same thing. But here what I wanted to show you is that...
Pranav sir, if he requires more time, let him go. Let him take.
No, I'm actually...
Please feel free to exceed.
No, if it's, I see, because there are...
No, sir, you can definitely show us these projects. In fact, there are already some questions that have come.
So please go ahead and take your time. We can exceed another 15 minutes, no problem.
Okay, thank you, sir. So this is, this is actually the fifth tower of the same complex. But why? The reason for showing you this is how the impact of DC rule changed the design of of a of a tower. Like if earlier what we had done is we have the similar tower on these two are as the same design as these three, because we wanted to use the same shuttering system, the same so because we get more repetition, it becomes highly economical to use it. But when we finished these three towers, the development control rules changed, and there was this fungible concept which came in. And these two towers are designed as per the new DCR, the fungible DCR, which is where you free of FSI areas which were there for the lobbies suddenly came into that 35% bracket. So how that has impacted the design of the building is something which I would like to show. Number one is that earlier, you had only one staircase block, 2-meter staircase. Now with the new DCR, you get like 2 staircases of 2 meters. That is change number one. Change number two is that all these deck areas were earlier free of FSI. So with the fungible rule that came into FSI, so now in the new design, we could not afford to give these large decks. So what we have done that because the USP of this design was these large decks. So what we did is that we only restricted it only to the living room area, and the area in front of the bedrooms was taken to make the bedrooms larger. That was another change which happened. So if you see, it's only in front of the living rooms. So that was another change. Now there's a third change which has come is that refuge. These are these fire chutes which have gone away, and there is a fire lift which has been introduced in the new DCR. So you have to have a lift which is from the mid landing. So the firemen can come up from the mid landing, and this has to be alternate power supply needs to be connected to this lift. So in case of a blackout, this lift is operational. So this is the formwork which is happening, which is under the slip. It's like an all concrete formwork system, which is like it's an Malaysian formwork system. So the entire tower is in concrete. The structural design of this project is done by Girish Dravid. So we work very closely with him. Their firm Sterling was the structural consultants for this. Now this is again the fifth tower where you have the similar. Now what we have is that there is this PPL scheme, like where you have public car parking lot. So there is a rule where if you give a certain area of a car parking lot, 50% of that area you get as area to be built for the tower. So if suppose you are using say 2 lakh square feet in terms of a public car park which you hand over to the corporation, 1 lakh square feet you can build as a tower. So whatever you see, the blue is a public car park and the red is the car park for the tower. The red is the sale portion of the. That's basically, there are a lot of projects, the park or many projects have come under this scheme. So the blue is something which you hand over to the corporation, and red is the car park for the tower. So that fifth tower is like it's not like is not similar to the other four, but it has got this car parking tower which is basically tucked behind. and the top of this is a very large recreational space. So here you have these 4 towers which are already done. 1, 2, 3. Fourth one is behind this, and this is the 5th one which is now under construction. It's like basically a 60-story tower where you have the top of the multi-purpose the parking tower is basically all landscape. These are some renderings of that. This is now this is completed now. This was the rendering. This is under construction, but now it's completed. So there's so lot of recreational areas now in the new projects which we are designing. Basically, all the recreational is all above ground. Like it's all happening on podiums, terraces. Nothing is happening on the ground because there is no space on the ground. This is the public car park getting built. Now the tower is almost on the 30th slab. This is how it fits into the. These are the 4, 1, 2, 3, 4, and the 5th tower. The 5th one is also now just almost topping up. So that's just the statistics of the total construction is around 55 lakh square feet and cost is around 3,000 crores. Thank you, sir. Any other questions?
Hello. Thank you, sir, for the presentation. There are a few questions here. First question is by Professor Mandar Turi. He was asking if you could just elaborate about the special specification that one has to kind of consider while designing the tall buildings. What is the RCC mix for the foundations or the superstructures, or what are the different finishes for that matter that could be used, either the walls or the internal walls and the steel reinforcements, the specification for the steel reinforcement. Sir, you're on mute.
The specifications of the structural the specification of the structure basically is the purview of the structural consultant. So, but to answer your question, what we need to basically look at is, when you design a high-rise building, is that you cannot you have to design in a way that it's not like a short building where you can put a scaffolding and change the glass, or you can put in, if there's some kind of a leakage, you can amend the leakage. So those kind of things cannot be done in a high-rise building. So conceptually, when you're designing a high-rise building, it has to be that it is like a permanent solution. Whatever you do, it has to be everything. There's not going to be any maintenance on the facade other than maybe painting it after 5 years or 10 years. So it has to be a kind of, even in terms of cladding also, whatever you use in terms of the glass, in terms of your window systems, it has to be a permanent solution. Another very important thing in a high-rise building when we are designing the facade is that you have to, in terms of the Vivaria project which I showed you, is that the way you design your, the window systems, it's important to see how you are going to clean it, from the outside. Now there are new towers which we are designing where we have like a window system which is built on the external, on the facade itself. But these are just normal window systems. So the way you open the windows and you clean it this all has to be pre-designed. You cannot do it, later on. And as I told, the Windows system is something which people pay a lot of attention to, because that's the only way something can go wrong, or there can be any leakages in the building. Because other than the window, everything is concrete. So next best thing is the window systems. They pay a lot of, so high rise and the window design is something which is very has to be done with lot of thought. You need a good budget for those window systems also.
Okay.
Because every 7 floors, the window sections change. After you go up 70 meters, every 7 floors, the system specification of the window changes. The thicknesses, everything changes. The glass thicknesses.
Okay. Okay, sir. So most of this is a question from my end. So most of the projects that you have highlighted here are residential projects. So if you could just give us a quick insights about, the mixed use projects with mixed use, commercial and residential.
Yeah, so see, the mixed use now earlier, before the 234 DCR, it was not very, the corporation was not encouraging mixed use development in a single building. Mixed use development in a plot was encouraged, but not in a single building. The reason, because you needed certain, suppose if you have residential and commercial together, your cores have to be separate. The people movements have to be separate. Car parking have to be separate. Plus, today there is another, legality is that even the societies need to be separate. So now because of the new trend, now in the current DCR, commercial has got 5 FSI. So there are exploring, mixed use kind of structures, but it's not happening much in what was happening abroad. Like hardly you can say 1% of the projects are developed as mixed use within the structure, not within the property. It's like one building has got like 2 or 3 kind of users in the same tower.
Okay, Pranav, can I ask this question?
Yeah, sure.
Yeah. Okay, Pranav, I just want to ask you, when you started phase 1 Vivaria, and now when you mentioned that phase 2 Vivaria, as an architect, what did you find a difference as an architect when you were designing Vivaria, and the experience what you got through Vivaria, and when you are designing phase 2 of it, did you could you explore more? The wisdom was grown, or you had grown yourself as an architect, or you could see that product in a different way, or what would you say that? What was a change which you could observe in yourself when you are designing phase 2? I understand the bylaws must have narrated everything and the design brief, but then there are certain things we grow as an professional. So what if you want to express, or maybe any other project, maybe what you worked decade back, and when you're working decade back, what kind of a change you see?
So that's, basically in terms of the Vivaria thing model now, what first 3 towers were, basically built together. It was like all the 3 were coming up together. And there was this kind of a notion, it was developed as very large flats. It was very kind of flats in today's market. And there was this deck which was, free of FSI. So because it was free of FSI, the developers, went like, gung ho, okay, isme bhi do, bada. So once they did that, now that became the USP of the project. Everybody started loving that 8 feet deck, like entire deck is like facing the Arabian Sea and the race course. And suddenly what happened is that the DCR changed, and all that came into FSI. So the new towers, that had to be shrunk by say 1/5. Okay, so today also, if you see now, the first 3 towers are getting a better premium than the 4th and the 5th. Technologically, 4th and 5th are far ahead, because the type of systems which we have used in terms of glazing, materials which we have used, because all the mistakes which we did in the first 3 were basically rectified in 4th and the 5th. And the most important learning was the window systems, because in the first 3 we didn't pay much attention to the design, the detailing of the window system. We got a vendor, the high-end vendor, and we just told him to place windows. But we didn't go into the nitty-gritty of the detailing, the flashing, the way it was basically connected to the structure. So that all was in the 4th and the 5th. We did like a step sill detail, all around the window.
Absolutely.
So it was like a constant learning. But what is the transition which we felt is that from 1 to 5, the complexity of the structures have become more. And now after 5 also, which the new projects we are doing, it's like mind-boggling. It's like something which sometimes I wonder why the hell I'm doing something like that. But then you think, okay, I'm doing it, so I'll do it better than the others.
Absolutely right.
It is that kind of thing. Because now currently, one of the projects which I wanted to show the students is like a density of 20. Like you're designing a density of 20 on a plot which is 3,000 square meter. You're putting in a construction area of almost 20 lakhs square. So those are the kind of projects which they will have to design.
Okay, I think Aishwarya, there's one girl who has asked this question, and I'm just reading it, that she has asked that how exactly I should begin with a high-rise development. And I think this is a wonderful answer, that when you have a FSI of a 20 to consume on such a plot, it's something which is a challenge, and that drives you towards your solution. And as simple as that. I mean, if the question is asked that how to design, it's a challenge which is given to you, and within these parameters, what Pranav has shown, within those parameters, coming up with the solution and satisfying your developer is the biggest challenge, isn't it, Pranav?
See, my daughter was also studying architecture. So she once, told me that when you start your design, what do you think of? For the question, what is the first thing which comes to the mind?
Exactly. Her question is also this. I mean, let her ask that question.
Yes, she's coming online.
Yes, Aishwarya, can you unmute yourself?
Aishwarya, unmute yourself. You're on mute.
Yes, sir. So I'm a little curious about how you start to design, because this is the first project of tall building, and how to start and begin with this.
As I was just coming to that, like everybody feels like, you start by, even when you present to the clients, what we show is that site context. The road is from here, and sun path and wind direction. All that we show in our presentation. But that's not where actually we start. The sustainability parameters is the last thing which comes into mind. I'm being a little like harsh, but sustainability comes like very, 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 very down into the list. The first parameter is like if it's a residential building you're designing, or an office building you're designing. Like if you had to buy a flat into that, like what will be your parameter? Whether you would go for a building which is like 2 flats, you will have 1 neighbor, 6 neighbors. If you see out of your window, you would like to see a sea. You would like to see another 30-story building next to you. would you like to see? So those kind of parameters first come into your mind, because that is how you start thinking, because ultimately the end user is the king. Like suppose you design something and nobody wants to stay in it, means you have not done your job well. So whenever you design something, it has to be liked by the person who's going to actually use it. That's parameter number one. Once you fit into that, then all the other parameters like your structural design, MEP, sustainability, all those parameters will automatically start fitting in. If your principally that is wrong, the first is wrong, then you will not, basically be able to build a successful project. So everybody says, wind direction, you have to see wind direction, but that is not the thing which you see first. The first is how you want, what are the market forces which govern your design? Is it your sizing? Is it like now in one of the projects which I wanted to show you, we were, there was this Chandanwadi cemetery was like in front of the plot. So in front of Chandanwadi is full sea view. So how do you, there's a psyche कि अरे मेरे को मेरा स्मशान नहीं दिखना चाहिए. So your design starts with that in mind. कि स्मशान भी नहीं दिखना चाहिए, लेकिन sea view भी मिलना चाहिए. So once you basically break that, or once you solve that, then everything fits in. Then structural designer will come and say, हाँ ये तो मैं कर सकता है, ये नहीं कर सकता है, ये नियम निकालो. So those are all nitty-gritties. But conceptually you have to be very strong in terms of what the end user wants. It can be an office, it can be a home, it can be anything. Like normally high rises are either homes or offices. Very few we have mixed use developments. Hotels to some extent, yes.
So first you consider the services.
No, services comes last. First is your what you're building for. That is the first thing you see. Like suppose you like now, for example, if you have a good view on the south, for example, your sustainability, your green homes person will say, "नहीं उधर glass मत रखो."
Actually, Ankur said the same thing, because he said that Mumbai has a sea on the west and everybody wants a west view, and that's where you provide the glass. So that's where the biggest challenge is for us.
We had one project where the south had the best view. So that means should I do a dead wall on the south?
So, sir, just in the last example, the Mahalakshmi racecourse example you showed. Yes, the west facing would be the sea. Now, this is where a student would have to understand that, okay, when a theory says west facade should be obstructed because of harsh light. Now, what Pranav sir said, that market forces. Now, that is a client's owner. If you were there, if you were buying a house, you will always say, मेरे को CBU चाहिए. उसके बिना मैं खरीदेगा नहीं. अगर if you would have decided कि मेरे को back side दिखाना है, probably no one will buy the house. So these are the market forces, are these, the decision making, that, okay, now as an architect, then you will have to play a role. I would not say this is first or this is second or this is third, but yes, you would have to compromise on the west facade, that I will have to design it better through additional resources, through a better shading device or a better glass or something else. Now, those are decision making which you will have to get intervene. That is your decision making power. That, okay, I am compromising west or south, as said in one of the projects. Madam said in one of the projects, south was a harsh thing and you had to work on it and you had to face south. You cannot give that out. I 200% agree. But then your responsibility comes as an individual, as an architect, that how do you balance it out?
Exactly. Perfectly. Well said.
Yeah, and if I have
And
to add something.
also, I would take a stand that probably services, probably in the market, a service consultant would have come much later, because probably architect in the back of the mind has already taken into consideration certain services. So if you say this is first, this is second, this is third, this is fourth, so मैं services last day as a student अगर करूँगी, probably you will realize this design cannot be resolved.
Correct. So,
So you
that's
will
what.
have to integrate. That is where we are working as an institution, where integration is at the services also is parallelly at the back of the mind. There is a back end. So पहले तुम उसको market force को compromise नहीं कर सकते. लेकिन back of the mind में तुम्हें वो चीज रखना है, those aspects, the allied. So what you saw from yesterday till today, before Pranav presented, were all the things which have to be run parallelly.
So, as rightly said by Sir, and what Pranav was trying to say is this: we are so technically now matured that we know that what is the size of LV shaft is going to come for 50-story tall building.
Yeah, correct.
So I provide that shaft size, and I know how much portion of it is going to come into FSI when he's talking about fungible. So I know there is one LV shaft. As Suraj said, that there could be a bus bar, or there could be electrical conduits which are running, cables running. I know there is a fire hydrant. I know I will have an elevator consultant who is analyzing and saying that so many number of elevators, and I know how to calculate number of floors for the elevator and mota-moti sizing and what is the staircase sizing. So we are technically well versed, and that's the benchmark. I mean, the question which I asked to Pranav is, you grow your wisdom. So maybe Viveria phase 1, he may have needed some other consultant, but then today the plan itself at the concept level is so matured that we know that tomorrow when the services consultant will come, he may ask for one additional chat, but nothing more than that. So we are prepared, and that's how we show it to the client. And the project which he's talking about is a very high density complex project where you have 33/7 is something which is a redevelopment. The challenge is immense. So when you have a larger master layout, you may have that flexibility to orient your building in that particular direction. So if I have 15 acres of land parcel,
yeah, exactly.
and if I have to have 10 buildings, then my challenge is less, because I have an opportunity to orient my building in that particular orientation. So, first of all, it's like actors. The role which has been given to me, I know whether I have to play a hero or heroine or vamp or bhabi or bhaiya, what it is. So that's how the genre of the project is defined. And based upon that, architect has to be flexible enough to mold himself into that particular mold. And that's where he's showing you a challenging project plus high rises. So challenge is 5 times. Even the piling on such sites is such a difficult task to have 3 basements, 4 basements. I mean, structural consultant to create that kind, and site guys to work in such conditions. So we work around all that, and that's where the maturity is established. So it's a process, and that's where he said that वो लास्ट में, लेकिन वो लास्ट में नहीं, when he is drawing his first line, he knows इधर मेरा सर्विस शाफ्ट आएगा, इधर मेरा HVAC यूनिट आएगा, इधर आउटडोर यूनिट आएगा, तो मेरा व्यू कैसे जाएगा, क्या होएगा, मेरा खिड़की कितना फ्रेंच विंडो आएगा, या I'll have a sill. All that is there, which has been worked out. We know that this is how we have to deal with it. So when the concept goes, it is almost at the schematic level, and that's where we reach, because we have been facing this for past several years and struggling into it.
Now that Excalibur project which I showed you, like it's basically a 33/7 project. So when we started with the design, the first parameter was that we want the sale building separate and the rehab building separate. So that was parameter number 1. Parameter number 2 is that if I tilt my sale building to a certain angle, like say 30 degree, I get unobstructed view of the race course. But that was like the most ideal most ideal thing to do. But the moment I do that, if I tilt that building in that small site, what I get these triangular residual spaces. So because of that, my parking is not yet becoming efficient.
Correct.
So I didn't tilt the building, I kept it parallel to the plot itself. So you have to weigh the pros and cons. So even by putting it parallel, you are still getting view of the race course, but you're not getting like a bang on view of the race course. So those you will, when you're designing, you will be always shifting. Your mind is always ye better hai, ye better hai. So your decision making has to be very fast. Okay, this is more important than this, so let me work on this. So it has to be very practical in terms of the way you design. And as Anuja said, like with experience, we know that how many lifts are going to, the size of the shafts, what is FSI, what is not FSI. That will come with experience. Once you do like 2 or 3 more plans, you will get it. It's no rocket science. It's nothing like great, yeah. But you will always have to like weigh, okay, this is more important. Okay, let me compromise the view a bit, but give more efficient parking. Or in some cases, it may be no, let me not make an inefficient parking, but let me do the better views. See, every project has a different way of dealing. So it's like project to project.
Yeah, and even as an architect, we do a lot of market study. It's a socio-economic studies we have been doing. So when developer comes to us, even we know area-wise what kind. I mean, if tomorrow he says Mahalakshmi Race Course view with a west view, I will do studio apartment, nobody's going to buy. He knows that Vivarea has to be 3 BHK, 4 BHK, that kind of luxury product. So even area-wise, your product are going to differ.
Yeah.
So even that study, we do it closely. I mean, that's how we develop ourselves, by studying that what developer wants, what customer wants, how developer is looking at the efficiency. And even there you go hand in hand with structural consulting, because you know whether you want to go with the columns or you want to go with the shear walls or you want to go with the structural walls, and all that decision making is a process. It's a charrette, it's a teamwork. So that's how the entire process happens. So it's not a single-handedly process, but there are so many inputs you're receiving from all 360 degree, and architect is, as Suraj has shown you, that he's a captain of the ship.
Yeah.
So architect needs to understand everything, and he should have a control of all the, I mean, tomorrow, Pranav and we know that how the STP functions. If that we don't know, we cannot design the space. So even what horsepower pump is going to be, fire pump, we all know. What is the size of the pump room, how to access that. Everything we know, because unless and until we study that, it's not possible to deal with it. So that's how we design. As simple as that.
Correct.
Yes, sir. Our next question is by a student, Ritika. She's asking how to avoid rain from coming within the interior spaces of the top floors. Because normally with the window openings, she was kind of facing some personal experience that there is, even in the downpour, how do you cater to the window sizes and the openings on the higher floors?
Oh, so what as I said that like when you're doing high rises, like most, like other than your window openings, everything is concrete. So there are very less chances of water seeping through the concrete. Where the real problem comes is the joinery, the joint between your window system and your RCC. That's where the leakages happen. Another thing is that currently there is this trend of avoiding chhattas above windows, because it looks like it's like either old-fashioned or ugly or whatever. So, but that chhatta system what we had is something which is like a kind of a tried and tested concept. So there are many places, like I'm not talking about the high-rise buildings, I'm talking about like say low-rise 12-story buildings where in certain places we have not provided chhattas, and that is where you get maximum problems. Other thing is now the window systems are so advanced in terms of their detailing, in terms of their finishing, is that you get a lot of things which are inbuilt, like your flashing is inbuilt, your drainage system is inbuilt. Even if you don't have a chacha, your top your openings are all covered by flashings and things like that. So the developers who are doing high-rise buildings, they basically evaluate window systems almost 2 years before they are actually getting installed. They go to these fairs, what is coming new in the market, and they negotiate. So if today, if you have to put their negotiations and their research would have started 2 years, ahead of time. And now there are these glass curtain walling buildings. Even in residentials, you see many of the buildings which are glass buildings. So there the leakage problems are relatively less, but the negative part is that they don't have cross ventilation in their apartments. Your the windows open like only 10% opening you have. Like normally a residential building needs at least 30% or 35% window openings for for proper ventilation. When you open like your one of the user feedbacks of Vivaria is that in the morning you can open the window and step into the balcony. So, like there are many glass buildings, you cannot do that. You have these small top hung windows. You just open them and then hardly you get any ventilation or things like that. So everything has to have like an Indian context to it. Like, you have a lot of our culture is like cooking culture is like you have that tadka, you have cooking is like with spices. Is a lot of aroma in our cooking. So you cannot have like a very closed kind of a residential space. Because of that, it basically your whole house basically smells in terms of your and there are certain kitchens which are they're inside the house. There are many residential buildings which are designed like that with glass in front. So those are not very well accepted. There are developers who are doing it, but it's not a very, very happy situation. So till today, even in high rises, people there are preferring some kind of a ventilation, and with this COVID world, that has even gone up more because now they want that balconies to come back. There are now certain developers who are actually taking balconies in FSI and building, asking us, okay, take it in FSI, let's give balconies. So those trends have totally changed in 2 years.
Okay, sir. Yeah, I think we've answered most of the questions. Do we have anything more? So yeah, over to Shruti.
Yeah, thank you so much, sir. It was a wonderful presentation, and I think the question answer session was also very interactive and lively with participation from Anuja ma'am as well. So it was very nice. Thank you so much. On behalf of ESCO, we would like to present you with a small digital memento. I request. Here it is. Thank you so much, sir, for
Thanks
taking
a
your
lot.
time.
Thanks a lot.
We really appreciate it.
Thank you, Anand sir.
Thank you, Pranav. Thanks a lot for taking out time. And
anytime, sir, anytime.
Thank you. So with this, we come to an end. With this, we come to an end to the presentations. It was a delightful 2 days with many experts from the industry coming together on one single platform to give a holistic perspective on the approach to tall building design. The 2 days saw some very interactive sessions between speakers and students, and we're sure that this is going to provide the students with the much required insight for their own design projects this semester. Thank you so much. Before I conclude, I would request Professor Achari to say a few words.
Yeah, thank you, Shruti. Yes, very delightful and very informative and very rich level of discussions which happened in last 2 days. Probably a multi-dimensional look which each one of you will remember this for your life probably, about how to approach a particular design. And there are, as Anuja madam has said, it's a chariot and it's a multi-architect who becomes a captain of that ship where multiple people they have to work with. So you could see that multi-dimensions. Actually, when you go, probably you would not see 7, 8, probably it goes to 15, 20 or 25 consultants on board in a project like this. But finally, you have to play this role play, what we call role play. Each one of you will have to understand what the other consultant would have to go through and or what they would be requiring, understand that and start applying into the design. So you need not be an expert by thing, but if you don't know that, you can't design. It's like that. So you need to understand each requirement of an MEP or a structure or a the other consultants, fire consultants, and so on. So hope these 2 days have given enough inputs for you to take lead in the coming design studio. And we look forward and we thank the entire CTBUH team, executive committee, and also the entire executive committee, including Mr. Girish Dravid, Vice Chairman, also Mr. Anil Hita, and the entire team. It was wonderful to open-heartedly accept our invite and come forward and support the college to understand the various aspects which goes in doing a project like this scale. And I thank all the speakers who beautifully presented their approach and their insights, their experience here. I hope our one wish of having a site visit can be taken care if during this COVID times. If it is possible, we'll try our best with looking forward for permissions and students' preparedness. And on behalf of the entire management, VES management, and behalf of entire faculty and students, we thank you.
Yeah.
Thanks for this, and thank all the students for that patient listening. I hope it has given a good food for thought for the next 6 months.
Yeah, so on behalf of Girish, Anil, and entire executive committee of Nikhil Sanghvi, Subodh Arora, Yogesh Hate, Dak Matthew, and myself, I thank all the speakers, all the student and the coordinating staff, and Principal Achari. Thank you for all this exciting journey, what we had 2 days. And I think students, I can see the excitement on the students when they are participating in the high-rise competition, and do a lot of your own researches, because there's so much excitement happening worldwide and which could excite you. So dream, design, and think out of box, but at the same time, think practically. That's what I would like to say to all of you. All the best.
And thanks to all the coordinating team from Shruti, Shrutika, Jinisha, Ajit, Vikrant, and all the other backend team who are working to make this a success. Thanks.
Okay, bye. Have a great day, all of you. Bye.
Thank you.
Bye, Pranav.
Thank you.
Bye,
Thank you.
Mandar.
Thank you.